A cold, dark object drifts through space, its path slow and steady. From a distance, it looks like a comet. Scientists see the faint glow of reflected sunlight and the long trail of dust behind it. They mark its orbit, predict its course, and move on to the next observation. Space is full of rocks and ice, and most of them are harmless. The data matches what they expect, so no one asks deeper questions. It is easy to believe it is only what it appears to be. This is how danger hides in plain sight. A comet is common. Familiar, it has no engines, no metal, no signs of design. It does not send signals or change speed. When something fits our idea of normal, we rarely stop to think about what else it might be. That gap in thinking leaves room for something worse to slip through. Imagine an object built to look natural but designed with intent. It could be a vessel, a probe, or a weapon. If it copies the outward features of a comet, we might never suspect its true purpose until it is too late. Think about the early days of space exploration. Astronomers saw faint dots of light on their screens. They identified asteroids and comets by their motion. These observations relied on patterns built from years of study. A comet has a predictable orbit and a specific kind of tail. If an object behaves that way, it is logged as such without question. Now imagine a clever engineer, somewhere out there, aware of our methods. They could design an object that matches these patterns perfectly. Its hull could be coated with frozen water and dust. Its shape could mimic natural bodies. Sensors on Earth would see what they expect to see. Nothing would seem out of place. Picture this scenario. A team at a small observatory tracks a new object. It moves on a wide orbit around the Sun. Its speed matches that of other comets. The computer model marks it as unimportant. Months pass. The object draws closer. No alarms go off because it behaves exactly as a harmless comet should, but hidden beneath its frozen crust is a chamber holding machines or microbes. When it reaches a certain distance, heat from the Sun melts the outer layer, releasing what waits inside. By the time anyone notices unusual activity, the release has already begun. The initial misidentification allows the threat to unfold without resistance. This problem extends beyond space. The same thing happens on Earth when people mistake one thing for another. A package left on a street corner might look like trash, but it could hide explosives. A digital file might appear as harmless text while carrying malware deep in its code. The danger lies not only in the object itself, but in our assumptions. When we see something familiar, we relax. That moment of relaxation gives a hidden threat the time it needs. The psychology behind this is simple. Humans are wired to save energy. We categorize objects quickly. If something looks like what we know, we do not waste time investigating. In daily life, this habit works well. It keeps us from being overwhelmed by endless details. But in fields like space exploration, defense, or disease control, that habit can blind us. We see what we expect instead of what is truly there. A comet that is not a comet fits this pattern perfectly. Its disguise is effective because it plays into our instinct to trust appearances. Consider how much trust we place in machines. Telescopes gather data. Computers analyze it, and the results appear on screens. Scientists rely on algorithms to sort through mountains of information. If an object fits the profile of a comet, the system files it as such without extra steps. No human may ever look at the raw data. This efficiency helps track thousands of objects, but it also creates weakness. A designed object that mimics a comet slips through unnoticed because the machines are built to follow rules, not question them. There are historical parallels. During the Cold War, military planners worried about missiles hidden inside cargo ships or disguised as civilian aircraft. It only needed to be good enough to buy time. A plane painted with commercial markings could cross borders without drawing fire. By the time its true purpose became clear, it would already be too late to stop it. The same principle applies to space. If something engineered travels under the mask of a comet, the early warning systems fail. Think of the first time scientists saw Oumuamua, the elongated object that passed through our solar system. Its odd shape and speed sparked a debate. Some wondered if it was artificial. Most experts dismissed that idea because there was no evidence beyond unusual movement. They settled on calling it a comet or asteroid, even though it did not fit perfectly. That decision reflects how strong our need for familiar labels is. It feels safer to say, just a comet, than to admit we might not know what we are looking at. The label ends the conversation and closes the door to other possibilities. The danger is not only physical. Misidentifying an object can lead to wrong choices on a global scale. If a threat arrives and is ignored, plans are delayed. Resources are not mobilized. Governments may argue instead of acting by the time evidence forces action. The damage is done. The initial error of calling something harmless ripples outward, affecting everything that follows. Even if people later realize the truth, the lost time cannot be recovered. To avoid this trap, one must imagine worst case scenarios even when evidence seems thin. This is not about paranoia, it is about discipline. If an object in space behaves exactly like a comet, we should still ask if it could be something else. That question must remain open until proven false. Engineers should test whether a device could mimic natural signals. Scientists should study ways to detect hidden payloads beneath ice or rock. These steps take extra effort, but they close the gap that a dangerous actor might exploit. Imagine again the first object we discussed, drifting through the dark. Now, instead of a quiet dismissal, imagine a team digging deeper. They noticed tiny irregularities in its surface, signs too small for automated systems to catch. They track it more closely, sending probes to scan it directly. When they discover the hidden chamber, they have time to respond. The object never gets close enough to release its payload. The difference between disaster and safety comes down to one choice: whether to accept appearances or question them. The risk of mistaking danger for safety will never disappear. As technology advances, disguises will grow more convincing. Objects designed to deceive will blend more easily with their surroundings. The only defense is constant vigilance. A comet is usually a comet, but sometimes, rarely, it is not. Those rare cases are the ones that matter most, because they hold the power to change everything. A dark object moves through space on a path that astronomers have tracked for months. Its motion follows the rules of gravity. Observers calculate its orbit using the known pull of the Sun, planets, and other nearby bodies. Each night, they check its position and see that the numbers match their predictions. This builds trust. People believe they understand where it is going and when it will. They plan around this belief, confident that nothing unexpected will happen. Then, one night, the object is not where it should be. It has shifted slightly, just enough to cause alarm. The change is small at first, a matter of a few kilometers. Computers recalculate and adjust the orbit. The new path still seems safe, though a little less certain. A few days later, the object shifts again, this time much more. Now the predicted models fail entirely. The path veers closer to Earth or another target. The cause is unknown, and the timeline for action grows short. This scenario can happen when an object experiences non-gravitational forces. Unlike gravity, which acts in a steady, predictable way, these forces can appear suddenly. For comets, the most common source is outgassing. As a comet nears the Sun, heat causes frozen material on its surface to vaporize. The gas escapes into space, pushing back on the comet. If the gas escapes evenly from all sides, the effect balances out. But when the venting happens more strongly on one side than another, the result is an unplanned thrust. Even a small thrust applied over days or weeks can change a comet's trajectory by thousands of kilometers. Imagine a comet with several vents on its surface. Some vents are buried deep under layers of dust and ice. Others are wide open. When sunlight strikes the comet, only the exposed vents release gas. As the comet rotates, the sunlight shifts, heating different regions at different times. This creates pulses of force that vary from hour to hour. Scientists tracking the object may not see this process directly. They only see its position changing in ways their models cannot explain. The comet's motion no longer fits the simple math of gravity alone. These perturbations can be subtle at first. A change of a fraction of a millimeter per second may seem unimportant, but over millions of kilometers, that tiny push adds up. Picture a spacecraft aimed at a planet. If its initial course is slightly off, the final error at arrival can be enormous. The same is true for a comet. When a path shifts early, even by a small amount, the final destination may be completely different. A near miss can become a direct hit without warning. In the past, astronomers have seen these sudden shifts many times. The comet Shoemaker, Levy 9, broke into pieces because of Jupiter's gravity. After the breakup, the fragments outgassed at different rates, causing them to drift apart unpredictably. By the time the pieces reached Jupiter, their impacts were spread out across the planet's surface. This unpredictability made early predictions difficult. Similar surprises have occurred with other comets as well. Each case shows how sensitive these bodies are to forces beyond gravity. Now consider a situation where the outgassing is not natural. Imagine a hidden mechanism buried inside the object. It releases material at specific times, mimicking natural behavior at first. Observers see the venting and assume it is random, like any other comet. But this controlled release could steer the object deliberately. To outside observers, the motion looks chaotic. In reality, it follows a hidden plan. This possibility complicates the task of tracking and predicting. If no one suspects intent, they will treat each shift as a natural error, not a signal of control. Tracking such objects relies on constant observation. Radar, optical telescopes, and infrared sensors all gather data. These measurements feed into computer models that predict future positions. The models assume known forces, gravity, sunlight pressure, and basic outgassing patterns. When something falls outside those assumptions, the predictions break down. This breakdown causes cascading problems. Space agencies may waste fuel moving spacecraft into the wrong positions. Defense systems may prepare for threats in the wrong locations. Governments may argue over conflicting reports, losing precious time. Imagine a team monitoring an object heading near Earth. Early projections show it will pass at a safe distance. Weeks later, new data shows a slight drift toward a closer approach. Analysts scramble to explain the change. Some suggest measurement error, others blame uneven outgassing. While they debate, the object continues to shift. Suddenly, with only days remaining, its path crosses into a collision course. There is little time left for deflection or evacuation. What began as a small error grows into a full crisis. This risk is not just about physical impact. Satellites and spacecraft depend on accurate trajectory forecasts. A sudden deviation could put valuable equipment in danger. It could also disrupt communication and navigation networks if debris spreads through key orbital zones. Even without a direct hit, the uncertainty alone causes chaos. Launches might be delayed. Missions could be cancelled. Insurance costs would rise. The economic and political ripple effects could be immense. To reduce these risks, some teams run alternate models. These models include possible non-gravitational forces. They simulate different outgassing rates, surface shapes, and spin patterns. By comparing these models to real observations, scientists try to narrow the range of outcomes. This approach works well when there is plenty of data and time. But for newly discovered objects, especially those seen only weeks before a close pass, the window is too short. Unknowns dominate the math, leaving wide margins of error. Consider how this feels to the people involved. A small research group at a mountain observatory first spots the object. They send their data to a central tracking center. The center logs it and shares the orbit with other teams. As updates flow in, each group uses its own software and assumptions. At first, everyone agrees. The numbers match, and the danger seems low. Then a single observation shows a mismatch. A telescope records the object slightly ahead of schedule. At first, the team blames a clock error or cloud interference. But the pattern repeats, and other telescopes confirm it. Suddenly, there is no agreement. Some models show safety, others show impact. Decision: makers must choose which to believe, knowing the wrong choice could be catastrophic. The challenge grows when the source of the non-gravitational force is invisible. For example, a jet of gas may erupt only on the far side of the object, hidden from view. It could also vent material that is transparent or faint, making it undetectable. Without direct observation, scientists must infer its existence from the motion alone. This is like trying to guess the wind's strength by watching a drifting balloon. The effect is clear, but the cause remains uncertain. Further complication comes from the object's rotation. As it spins, the direction of thrust changes constantly. One moment, a jet pushes the object forward. Hours later, the same jet pushes sideways or backward. This produces a wobbling motion that defies simple prediction. Even small errors in measuring the spin period can lead to large errors in trajectory forecasts. As the object moves closer to the sun, the outgassing intensifies. The changes grow more dramatic. What was once a stable, predictable path now curves sharply. Observers struggle to keep up, updating their models multiple times a day. Each update narrows the window for response. If the object poses a threat, decisions must be made quickly. And with incomplete information, the situation becomes a race against time, where every observation matters and every hour counts. An object drifts silently through space, moving along a path shaped by gravity alone. From every measurement, it behaves like a comet or asteroid. Its surface reflects light in a way that looks natural. Telescopes track it night after night, feeding data into orbital models. The numbers match. Everything appears normal. Scientists predict where it will be weeks and months in advance with calm certainty. Plans are made based on these predictions. No one expects it to change course on its own because natural objects do not do that. They only move where gravity pushes them. Then, without warning, something happens. The object fires a burst of energy so faint it almost escapes detection. For a brief moment, its speed changes. The change is small, but it is deliberate. Hours later, it fires again, this time more strongly. The trajectory shifts in a way no natural force can explain. What everyone assumed to be a lifeless rock now behaves like a machine. This realization comes too late. By the time the data reaches decision makers, the object has already altered its course to move toward a target. Hidden propulsion systems pose a unique danger because they remain inactive for most of the journey. A spacecraft with engines that fire continuously would be easy to spot. Heat signatures, exhaust trails, or unexpected motion would reveal its true nature early on. But if the propulsion stays cold and quiet, buried under layers of dust and ice, the object appears inert. It blends in with the thousands of comets and asteroids tracked every year. Even close, Up images might show nothing unusual. Imagine a vessel designed to masquerade as a comet. Its outer shell is covered in frozen water and rock fragments, creating a natural-looking surface. Beneath this shell lie propulsion units and control systems, completely sealed off from view. For months or even years, the vessel drifts silently. Its path follows the rules of gravity exactly, because nothing artificial is active. Observers see no reason to suspect anything more than a harmless chunk of debris. The key moment comes when the vessel nears its destination. As it approaches a planet or moon, a signal triggers the hidden systems. Thrusters ignite for the first time. These thrusters could use low heat exhaust or directed particle streams to avoid detection. The sudden change in motion would confuse tracking systems. Predictions based on a purely natural trajectory would fail instantly. By the time analysts realize what has happened, the vessel could already be close enough to strike or deploy its payload. Consider how this would play out on Earth. Early detection programs spot an object moving inward from the outer solar system. Observatories log its speed and position, confirming it will pass harmlessly by at a wide distance. Governments and space agencies are notified, but no special action is taken. The object stays quiet for months. Then, when it reaches a certain point, its engines activate. Its new path brings it much closer than anyone expected. Initial reports blame unmodeled natural forces like outgassing or solar radiation. Hours later, radar data shows precise, deliberate maneuvers. The truth becomes clear. This is not a natural body at all. Panic spreads as people realize there is no plan in place to respond. The challenge grows worse if the control system inside the object is highly advanced. A basic thruster might only provide small bursts of acceleration. A more sophisticated system could perform complex maneuvers, dodging interceptors or changing course multiple times to hide its intent. It could even cut power suddenly, drifting again to mimic natural behavior before firing up at the last possible moment. Such tactics would create confusion among those trying to track it. Each shift would force new calculations, delaying any coordinated response. This problem is similar to military deception on Earth. A submarine hides beneath the ocean's surface, moving quietly to avoid sonar. A stealth aircraft flies low to stay below radar detection. These tactics rely on staying unseen until the last moment, when sudden action gives the attacker an overwhelming advantage. A hidden propulsion system in space uses the same principle. It hides under the vast cover of natural motion, then strikes with precision when ready. Detecting a hidden system requires more than watching an object's position. It demands close study of its energy output, surface heat, and chemical composition. Infrared sensors might detect faint warmth leaking from machinery, even when the engines are off. Spectral analysis of the object's tail or surface could reveal artificial materials mixed with natural dust. But these methods require detailed, high-resolution data. For distant objects, that data may not exist until the threat is already close. Imagine a scenario where a probe is sent to investigate. The probe approaches carefully, scanning for signs of life or technology. The disguised vessel remains still, giving no hint of danger. As the probe draws near, the vessel's systems activate. A rapid burst of acceleration pushes it past the probe before any images can be sent back. In one instant, the investigators lose both their equipment and their chance to warn others. Even if a hidden propulsion system is discovered, responding to it is difficult. Space is vast, and travel takes time. Interceptors or defensive satellites cannot move quickly enough to match sudden course changes. A threat that seems far away one week could be near the next. Without early detection, options shrink. Governments might consider nuclear deflection, but aiming such a strike at an actively maneuvering target would be extremely challenging. The first signs of hidden control could be subtle. A small, unexplained change in velocity might appear in the tracking data. Analysts might dismiss it as a measurement error or a natural venting event. Later, a series of similar changes would form a pattern too precise to ignore. By then, the object could be well inside the safe zone, moving with intent toward populated areas or valuable infrastructure in orbit. This scenario forces difficult decisions. If the object is artificial, who built it and why? Is it a weapon, a probe, or a warning? With no communication, those questions go unanswered. Leaders must act without full knowledge, choosing between caution and defense. A false alarm could cause widespread fear and waste resources. A delay could lead to disaster. Picture a final moment of realization. Tracking stations worldwide see the object's trajectory shift sharply. Instead of passing harmlessly by, it now aims straight for Earth. Within hours, more changes confirm that it is actively steering. Governments scramble to respond, but there is no time to launch new missions. The object draws closer, silent and cold on the outside, hiding machinery deep within. It has been there all along, hiding. The early assumptions, built on the belief that natural things stay natural, leave humanity unprepared for what comes next. A dark object moves silently through space, its surface covered with dust and frozen layers. From a distance, it looks like any other comet or asteroid. Light reflects off it in familiar ways, and its path through the solar system follows the rules of gravity. Observatories record its position, track its speed, and file it alongside thousands of other known bodies. Nothing about it stands out. When a mission is planned to study it, scientists expect to find common elements like carbon, oxygen, silicon, and iron. These are the building blocks of most natural bodies we have studied. The spacecraft arrives after years of travel and begins to collect samples. Small drills bite into the surface, pulling up frozen material and rock fragments. At first glance, everything seems routine. Cameras show grainy grey dust and fractured ice. The instruments measure simple compounds like water, methane, and carbon dioxide. These are normal readings, matching what scientists have seen before. Confidence grows that the mission will confirm existing theories about how comets form and evolve. The deeper analysis begins. As the samples are tested, strange results appear. Ratios of certain isotopes do not match anything recorded in known solar system materials. Elements appear that are rare or unstable under normal conditions. Some compounds react violently when exposed to the spacecraft's airlock environment, releasing unexpected energy. These reactions confuse the automated systems, which are built to handle only familiar chemistries. Alarms trigger as containment protocols struggle to keep up. On Earth, the data from these tests arrives with a delay. Scientists in control rooms study the numbers, frowning at the graphs. At first, they suspect instrument failure. A sensor might be miscalibrated, or a software bug might be creating false readings. They run checks and diagnostics, but everything comes back normal. The instruments are functioning correctly. The strange results are real. Something about the object's material is unlike anything seen before. Imagine a sample of rock that contains an element stable only at near absolute zero. As soon as it warms even slightly, it decays into new substances, releasing gases or heat in unpredictable ways. This would make it difficult to study using normal laboratory tools. A sealed container could fail without warning as the material transforms inside it. If such a sample were returned to Earth, it could threaten clean rooms, equipment, or even the safety of the people handling it. The unknown chemistry also complicates modeling. Planetary scientists rely on computer simulations to predict how comets and asteroids evolve. These models depend on known reaction rates, melting points, and structural behaviors. If the object's materials behave differently, the entire model collapses. For example, a layer of ice containing an exotic compound might sublimate much faster than expected, changing the way the object vents gas into space. This would affect its motion, surface shape, and lifespan. Predictions about its orbit would be wrong, leading to errors in long-term tracking. Consider how this might affect a mission like a sample return. A spacecraft is sent to collect material and bring it back for study. Engineers design storage containers, assuming that the samples will behave like those from past missions. They plan for known hazards such as dust abrasion or outgassing of familiar volatiles. If the samples contain unknown compounds, these precautions might not be enough. A reaction inside the container could damage the spacecraft on its return journey. If the reaction goes unnoticed, it could even trigger after landing, exposing laboratories and researchers to materials they are unprepared to handle. There is also the risk of contamination. Some of these unknown substances could interact with Earth's atmosphere or biosphere in harmful ways. Even a small amount of exotic material could disrupt ecosystems if it behaves differently from anything naturally occurring here. Imagine a compound that acts as a catalyst, speeding up chemical processes that normally take years or centuries if released. It could cause cascading reactions in soil, water, or air. This possibility forces strict quarantine procedures. But those procedures rely on knowing what to expect. If the hazard is truly alien, existing safeguards may fail. The history of science offers examples of similar surprises, though on a smaller scale. When early chemists isolated radioactive elements like radium and uranium, they did not fully understand the dangers. They handled the materials without protective gear, unaware of the long-term effects. By the time the risks were clear, people had already suffered harm. In a space mission context, an analogous mistake could happen on a much larger scale. Unknown chemistry from beyond Earth could pose dangers that are invisible until it is too late. Imagine the moment when the first unusual reading is confirmed. A laboratory technician sees a spectrum with peaks that do not correspond to any known element. She checks the calibration, repeats the test, and gets the same result. The news spreads quickly through the mission team. Meetings are called specialists debate whether the material could be artificial, a product of alien technology rather than natural processes. Others argue for natural explanations, suggesting that the element formed under conditions never seen before. The lack of information fuels both theories. Meanwhile, mission planners face immediate practical problems. The sample containers must be kept stable during the return trip. But no one knows what temperatures or pressures are safe. Some compounds might become volatile if cooled, while others might destabilize if warmed. Engineers work around the clock, trying to design emergency systems that can adapt on the fly. Every decision is made with limited data, raising the risk of failure. Back on Earth, governments and agencies argue over how to handle the arrival. Some push for strict isolation in underground facilities, fearing contamination. Others want faster access to the samples, hoping for technological breakthroughs. The debate grows tense as new readings arrive from the spacecraft, showing even more bizarre behaviors. One sample begins to emit radiation in a pattern that does not match any known decay chain. Another produces a gas that corrodes the containment seals faster than expected. These challenges extend beyond science and engineering. Political leaders must decide who controls the information. If the material has military potential, secrecy becomes a priority. If it poses a global hazard, transparency might be necessary to coordinate a response. Public reaction is another factor. News of truly alien chemistry could cause fear, excitement, or mistrust. Rumors might spread faster than facts, complicating efforts to maintain calm. Even the way the object itself is classified could change. At first, it is labeled a comet. Later, as the data grows stranger, some argue it might be a fragment of a larger structure, perhaps even a relic of a distant civilization. The debate over its origin affects every decision about how to study it. If the material is natural, it represents a new frontier of planetary science. If it is artificial, it suggests deliberate design and intent. Through all of this, one simple truth remains. Assumptions can be dangerous. Scientists expect certain ratios of elements, certain reactions, certain stable forms of matter. When those expectations fail, every step of the process becomes uncertain. Predictions falter, safety measures fail, and models collapse. An object with unknown chemistry challenges not only our understanding of space, but also our ability to protect ourselves from what we do not yet know. A silent object crosses the dark space between planets, moving at a steady speed. From a distance, it appears like a comet or asteroid, nothing more than ice and rock drifting through the void. Its surface reflects light in a dull, natural way. Telescopes track it and log its orbit with routine precision. The reports say it will pass by harmlessly, and attention shifts to other tasks. It is easy to dismiss because it behaves like countless other objects we have seen before. But what if this object is not just drifting? What if it has systems buried beneath its surface, watching as it approaches Earth? A probe built for surveillance would not need to make its presence obvious. It could hide its sensors under layers of dust and ice, masking heat and signals so completely that it appears lifeless. From afar, there would be no difference between this disguised machine and a true comet. Consider how advanced a probe like this might be. It could contain optical arrays hidden behind thin panels, using lenses or mirrors camouflaged to look like natural fractures. It might carry radio receivers designed to monitor our broadcasts without emitting a traceable signal. If it listens silently, there would be no way to detect it from the ground. As it draws closer, it could map radio traffic, satellite signals, and even radar emissions. The probe could learn how our networks are structured, what frequencies we use, and where our defenses are weakest, all without a single transmission to give itself away. Imagine this scenario. Months before the object arrives, a handful of amateur astronomers notice it in the night sky. They log its position and share their data. Larger observatories confirm the sighting and track its motion. Space agencies issue brief notices saying it poses no threat. It drifts quietly while interest fades. But as it nears Earth, the probe's systems wake up. Cameras activate, scanning the planet in high resolution. It captures images of cities, power grids, and launch sites. Its instruments detect every active transmission, building a complete picture of our technology. The key to this kind of mission is patience. A natural comet gives the perfect cover. People expect it to be there. They expect it to come close, pass by, and then move away. The very fact that it appears ordinary allows it to move freely. Unlike a spacecraft built openly for exploration, this probe does not need propulsion or constant control. Gravity carries it into position. Its hidden systems only activate when necessary, minimizing the risk of detection. Detection would be difficult even for modern instruments. Most space surveillance systems focus on objects that move unpredictably, such as satellites or debris in near-Earth orbit. A body on a long, stable trajectory is treated as background. Even if someone suspected unusual activity, they would need to prove it. A faint heat signature could be dismissed as a natural vent of gas. A slight change in motion might be blamed on uneven outgassing. The data always has natural explanations, which makes it easy to overlook the unnatural ones. Think about what happens once the probe begins active monitoring. It could deploy smaller devices like tiny drones to spread out and gather more detailed information. These devices might attach themselves to existing satellites, hiding among the equipment we already have in orbit. From there, They could intercept data streams or feed false information into our networks. This would give whoever built the probe a powerful advantage, all without revealing their presence. History shows how effective hidden observation can be. During the Cold War, submarines crept near enemy coastlines, listening to communications and tracking ship movements. Spy planes flew at the edge of detection, gathering photographs of bases and missile sites. The goal was always the same: to know more about the other side without starting a conflict. A spaceborne probe takes this concept to its extreme. It operates far above the reach of our current defenses, using distance and disguise as shields. Now picture the moment of realization. A research team studying data from a deep space telescope notices something odd. The object's surface shows unusual reflections, too regular to be random. When they analyze the patterns, they see shapes that resemble antenna arrays. They double. Check the data, thinking it must be a glitch. As they dig deeper, the evidence grows stronger. At first, they consider natural causes, like ice formations or unusual mineral deposits. But none of these explanations fit. Finally, someone voices the possibility that no one wants to say aloud. This might be a machine, not a rock. By the time they alert authorities, the probe has already completed much of its work. It has mapped the planet's defenses, tracked launch schedules, and identified vulnerabilities. Even if it never sends this information back to its creators, it could store it for later retrieval. A second object, arriving years later, could make direct contact and download everything. The implications are serious. If the probe is hostile, it may not be here only to observe. It could be positioning itself for a future mission. Knowing the layout of our satellites and power grids could make it easier to disable them later. Detailed maps of launch sites could help an attacker neutralize our space capabilities before we respond. Even if the probe itself never acts, the knowledge it gathers could shape future events in ways we cannot predict. Even a peaceful civilization might appear hostile through our eyes. If we do not know who sent the probe or why, fear will fill the gaps in our understanding. People will imagine worst-case scenarios. Governments will assume the object has military purpose. The lack of communication makes it impossible to resolve these fears calmly. Consider how people might react to this news. At first, most would dismiss it as rumor or conspiracy theory. The idea of an alien machine disguised as a comet sounds like fiction. But as more evidence comes out, detailed images, consistent patterns, unexplained signals, denial becomes harder. Panic could follow, especially if authorities cannot explain what is happening. Meanwhile, scientists and engineers face urgent challenges. They must track the probe with extreme precision, watching for any change in behavior. They must also develop ways to scan its emissions without alerting it to our efforts. This delicate balance requires coordination across multiple nations, many of whom may distrust each other. A mistake in communication could lead to conflict on Earth, even before anything happens in space. Imagine the probe's final maneuver. As it nears the end of its mission, it might shift into a stable orbit around the Moon or deep space near Earth. From this position, it could continue to watch indefinitely, its sensors powered by sunlight or internal energy reserves. It would not need to move again, only to observe and record. Over decades, it could track changes in our technology and society, updating its database silently. It would be a presence we could not remove, always there, always watching. The real danger lies not in a sudden attack, but in the slow, invisible gathering of knowledge. A hostile probe does not need weapons to change the balance of power. Information itself is a weapon. By knowing us better than we know it, the probe's creators would gain an advantage we might never overcome. And all of it could begin with a single, silent object, drifting through space, disguised as nothing more than a passing rock. A silent object drifts through space, cold and dark, appearing no different from countless comets and asteroids we track every year. It reflects sunlight in a natural pattern, its surface rough and uneven, covered with ice and dust. Telescopes watch it and predict its path with ease. It shows no signs of engines or deliberate motion. Astronomers catalogue it as routine, another visitor passing through the solar system. Weeks go by and interest fades. No one suspects it carries anything more than frozen debris. Deep inside, hidden beneath layers of rock and ice, are compartments packed with smaller devices. These microprobes are tiny, no larger than a fist or even a coin. Their surfaces are coated to match the material around them, so even if one were spotted, it would look like a harmless fragment. Each device is built to survive harsh conditions: vacuum, extreme cold, and radiation. They lie dormant, inactive, while the main body of the object travels undisturbed. From the outside, there is no clue that they exist. As the object approaches Earth, the compartments open quietly. The release happens in total silence, masked by the natural shedding of dust and gas that many comets produce when they warm near the Sun. To an observer on Earth, the event looks like a normal cometary outgassing, a natural plume of material breaking free. In reality, the object is deploying dozens or hundreds of microprobes into precise paths. Because they are so small and spread out, they are almost impossible to track. Radar might miss them completely, especially if they have surfaces designed to absorb or scatter signals. Each microprobe has a specific purpose. Some are designed to stay in space, entering low orbit around Earth or attaching themselves to existing satellites. Others are built to descend through the atmosphere. These might deploy heat-resistant shells or glide in on small wings, slowing enough to survive re-entry. Their tiny size allows them to avoid detection by early warning systems, which are tuned to look for larger objects like missiles or meteors. A microprobe could pass through the upper atmosphere without leaving a visible trail. Imagine one of these devices landing in a remote desert at night. It buries itself in the sand, sensors extending to monitor local signals. It begins transmitting data only when safe to do so, perhaps using low-power bursts that blend into background noise. Another lands in the ocean, floating just beneath the surface, collecting information about ship movements and underwater communications. Others scatter across high mountain ranges, cities, or even ice caps. Over time, they form a hidden network, silently mapping the planet. The challenge for detection is immense. Space agencies already track thousands of pieces of debris in orbit, but those objects are much larger. A microprobe, the size of a pebble, would not appear on standard systems. Even if one was seen, it might be mistaken for harmless space junk. In the atmosphere, the problem grows worse. Military radars focus on aircraft and missiles, not tiny devices falling silently through the sky. The probes could slip through these blind spots easily, especially during storms or heavy cloud cover. Consider a scenario where this happens without anyone noticing. The main object passes Earth at a safe distance. Observatories declare the encounter over. Scientists publish papers describing its orbit and composition. Meanwhile, the microprobes have already landed and begun their work. Weeks or months later, unusual signals appear in unexpected places. A remote weather station begins sending corrupted data. A communications satellite experiences small, unexplained glitches. Engineers blame natural wear or solar interference. No one thinks to connect these events to a single source. By the time the pattern becomes clear, the network of probes is well established and deeply embedded. These microprobes could have many functions beyond surveillance. Some might carry tiny drills or chemical samplers to study Earth's geology or atmosphere in ways invisible to our sensors. Others could be designed to interfere with technology. A probe attached to a satellite might alter its reading slightly, introducing false data without disabling the system outright. Over time, this could distort weather forecasts, navigation signals, or military communications. The effect would be subtle at first, spreading confusion slowly rather than causing immediate chaos. The idea of releasing many small devices has advantages over a single large spacecraft. A single machine can be destroyed or blocked if discovered. A swarm of microprobes is harder to fight. Even if a few are found and captured, others remain hidden. Their tiny size and passive design make them cheap and expendable. Losing some does not compromise the mission. This redundancy mirrors strategies used on Earth, like deploying multiple sensors across a battlefield or scattering surveillance drones over wide areas. Imagine a specific example. A microprobe lands on the roof of an urban building at night. It unfolds a thin antenna, no thicker than a hair, and begins listening to local radio and cellular traffic. The device transmits what it hears using brief encoded bursts, timed to coincide with natural interference like thunderstorms. Unless someone knows exactly when and where to look, the signal blends in with background noise. Another probe, hidden in orbit, receives these bursts and stores the data. Later, when the main body of the object or another craft passes by, it retrieves the stored information and carries it away. Even more concerning, some probes might have the ability to replicate or repair themselves using local materials. A device landing near a mine or industrial site could collect metals and chemicals, slowly building replacements for worn parts. Over time, a few probes could become many, spreading farther than their initial deployment range. This kind of growth would make containment almost impossible once the swarm was established. Detection efforts would face significant obstacles. Satellites would need to scan for unusual heat patterns, electromagnetic emissions, or chemical traces. Ground teams would have to search vast areas for objects smaller than a fist, often buried or camouflaged. The search could take years, with no guarantee of success. Meanwhile, the probes would continue their mission. This scenario also creates political problems. If the release is suspected but not proven, nations may accuse each other of hiding information or secretly deploying similar devices. The lack of clear evidence could lead to mistrust and conflict. Even if the true source lies far beyond Earth, humans might turn against each other while the real threat remains untouched. The initial response would likely focus on space surveillance. Observatories would re-examine data from the object's approach, looking for signs they missed. Analysts might find faint trails or unusual motions that suggest a controlled release. By then, the information would be historical. The probes would already be scattered, their locations unknown. This delay would make a coordinated defense nearly impossible. Imagine the moment when the first physical probe is finally found. A team hiking in a remote forest stumbles across a small, smooth object lodged in a tree. They bring it back to a lab, assuming it is a piece of meteorite. Under a microscope, its surface reveals intricate patterns, circuits, and moving parts far beyond known technology. The discovery sparks panic. If one probe is here, how many others are hidden elsewhere? Scientists and governments realized too late that the event they thought had ended was only the beginning. The release of microprobes from a disguised object combines stealth, scale, and patience. It does not require visible aggression or open conflict. It uses the natural environment as cover, hiding its actions inside ordinary patterns of dust, debris, and noise. The danger is not just in what the probes do individually, but in the network they form, a silent presence woven through space and Earth, operating unseen while everyone looks in the wrong direction. The object moves silently through space, cold and dark, looking like a comet or asteroid. Its path is steady, shaped by the pull of gravity alone. Telescopes track it without difficulty, and the data fits our models perfectly. Scientists predict its orbit months ahead, confident they know where it will be and when. From the surface, there is no reason to suspect anything unusual. The readings seem ordinary, the numbers stable, and the object unremarkable. Then the instruments start behaving strangely. A telescope records a sudden burst of static in its images. A radar station sees the object in one position, but another station, looking at the same time, reports it somewhere else. Satellites tracking it begin sending conflicting data. At first, these problems are blamed on equipment malfunctions or weather interference. Technicians run checks, recalibrate sensors, and repeat measurements. The anomalies persist. Each time the object comes into view, new problems arise. The possibility emerges that the object itself is causing these disruptions. If it carries a system capable of emitting electromagnetic signals, it could deliberately confuse our instruments. These signals might not look like obvious transmissions. Instead, they could take the form of faint, irregular pulses that blend into the background noise of space. Space is full of natural sources of radiation. Stars, cosmic rays, solar flares. A well-designed false signal could hide within this natural static, making it almost impossible to separate truth from deception. Imagine an object releasing low-level interference as it approaches. The emissions are tuned to specific frequencies used by tracking radars. These signals could create echoes that make the object appear to be in two places at once. Computers trying to plot its orbit would fail, producing wildly different predictions. Some models might show it moving harmlessly past Earth, while others predict a collision. With no clear decision, makers would be forced to act blindly, risking either false alarms or missed warnings. The effect could be even more subtle. Instead of creating obvious errors, the interference might slightly distort measurements. A telescope might record a false reading just a fraction off from reality. Over time, these small errors would accumulate, shifting the projected path slowly but steadily. By the time anyone noticed the drift, the real trajectory would be far from what was expected. This kind of manipulation could allow the object to approach undetected until the last possible moment. Consider a scenario involving multiple systems. Space agencies across different countries track the object using independent networks. Normally, they compare results to check for accuracy. If the interference affects each network in a slightly different way, their data would conflict. One nation's radar might show a safe distance, while another's telescope reports danger. Each side would suspect the other of error or deceit. Tension would grow as accusations fly. Meanwhile, the object continues its approach, using confusion as a shield. The interference could also disrupt unrelated systems. Communication satellites might experience brief outages when the object passes nearby. Navigation systems like GPS could give incorrect positions for aircraft or ships. At first, these problems would seem like isolated technical glitches. Only later, when patterns emerge, would investigators realize they all occurred when the object was overhead. By then, critical operations could have been affected, military movements delayed, rescue efforts misdirected, air traffic controllers overwhelmed by conflicting signals. Natural explanations would complicate the investigation. The sun often produces bursts of electromagnetic activity that interfere with electronics. Solar flares, geomagnetic storms, and cosmic rays can all cause sudden noise in sensors. A hostile signal could mimic these effects, making it indistinguishable from natural space weather. Analysts might waste precious time trying to determine whether a solar storm is to blame. The object could hide its actions behind this cover, knowing our systems are already used to dealing with background interference. Imagine a team working in a deep space observatory. They notice a repeating pattern in the noise, a faint pulse occurring at regular intervals. At first, They think it is an artifact of their equipment, perhaps a loose connection or a software bug. They test their systems, replacing components and rewriting code. The pattern remains. Slowly they realize it appears only when the object is in range. The signal is not random at all, it is deliberate. But by the time they understand this, the object is much closer than anyone thought. The interference might not just confuse measurements, it could actively hide the object's true nature. A probe equipped with advanced emitters could project false signatures. To radar, it might appear as a natural comet, with a cloud of harmless debris surrounding it. To infrared sensors, it could mimic the heat pattern of cold ice instead of warm machinery. These layers of deception would prevent analysts from identifying it as artificial. Even high-resolution images could be tampered with if the signal disrupts camera electronics at the right moment. Consider how this might unfold during a critical mission. A spacecraft is launched to intercept the object for study. As it approaches, its sensors begin to fail. Navigation readings fluctuate wildly, causing the spacecraft to veer off course. Communication with Earth cuts in and out. Filled with static operators on the ground, cannot tell whether the problems are mechanical or caused by the object itself. The mission falters, leaving no way to gather direct evidence. The object might also use interference as a weapon, not just a disguise. A strong burst of energy at the right frequency could disable satellites or fry unprotected circuits. Even a brief pulse could disrupt timing systems, throwing off everything from banking networks to power grids. This would not require large amounts of energy. A precisely tuned signal aimed at the right point could have cascading effects across global infrastructure. Imagine a coordinated attack where the object's false signals trigger at the same moment as a natural solar storm. The combined interference would overwhelm defenses. Engineers would struggle to separate natural from artificial effects. By the time they identified the source, critical systems could already be compromised. Detection of such signals would require constant monitoring across multiple frequencies. Specialized instruments would need to filter out natural background noise to look for patterns. Even then, the challenge would be immense. A clever emitter could change its pulse sequence, frequency, and strength regularly to avoid recognition. It might even mimic known satellites, making its transmissions seem like legitimate traffic. In one scenario, a single observatory finally records a clear signal. The pattern matches no known source and is traced back to the object. Scientists rush to publish their findings, but as soon as they do, the signal stops. Critics claim the data was a fluke or even fabricated. The lack of ongoing evidence makes it difficult to convince others. While debate rages, the object continues its mission unchallenged. False signals and electromagnetic interference turn our own systems against us. They exploit our reliance on technology, using noise and confusion as weapons. By twisting the data, the object controls what we see and what we believe. In this way, it could move freely through our space, carrying out its true purpose, while we argue over illusions created by its invisible hand. A dark object travels through space, silent and cold, carrying material that has never been near Earth. From a distance, it appears to be an ordinary comet or asteroid. Telescopes track it, and its orbit follows the predictable pull of gravity. As it moves closer, excitement grows among scientists eager to study it. Missions are proposed to intercept it, to take samples, and to bring pieces back for study. The potential for discovery is enormous. It could reveal how our solar system formed, or even contain clues about life beyond Earth. But with that excitement comes a risk. When two environments meet, contamination can flow in either direction. Forward contamination happens when material from Earth is introduced to the object. Backward contamination happens when material from the object is brought back to Earth. Both forms of contamination can have serious consequences. Forward contamination begins the moment we send a spacecraft to the object. No matter how carefully we sterilize equipment, it is almost impossible to remove every microbe. Tiny organisms can survive deep inside electronics or hidden in narrow crevices. Once the spacecraft reaches the object, those organisms could transfer to its surface. If the object contains untouched environments, our microbes could disrupt them. This would make it difficult to know whether any signs of life we detect are truly alien or just contaminants we brought with us. Imagine drilling into the object's surface to search for organic compounds. The drill bit might carry bacteria from Earth, even if it was sterilized before launch. When samples are analyzed, scientists could see traces of DNA and mistakenly believe they have found alien life. Years of work might be wasted chasing results that are nothing more than pollution from our own planet. Worse, if the object actually harbors its own fragile ecosystem, our contamination could destroy it before we ever detect it. Backward contamination is even more concerning. This happens when material from the object comes back to Earth. If that material contains unknown agents, viruses, spores, or chemicals, they could interact with our environment in dangerous ways. These agents might be harmless in space, but highly reactive in Earth's atmosphere or biosphere. Even a tiny amount could have unpredictable effects. Consider a sealed sample return capsule landing on Earth. Engineers design it to keep its contents isolated, but absolute security is difficult to guarantee. A small crack in the seal, invisible to the naked eye, could let microscopic particles escape. Wind or rain could then spread them before anyone realizes there is a problem. Once released, tracking and containing the material would be almost impossible. The history of science shows how easily contamination can occur. When early explorers traveled to new parts of Earth, they carried diseases to populations with no immunity. Entire ecosystems were disrupted by invasive species accidentally introduced. Through trade or travel, space exploration adds another layer of complexity because we have no prior experience with alien biology. If an organism evolved in complete isolation, it might interact with Earth's life in ways we cannot predict. Imagine a scenario where a sample brought back from space is opened in a secure laboratory. Scientists expect to see frozen dust and inert rock. Instead, a reaction begins when the sample is exposed to air. The material releases a gas never before encountered. At first, it seems harmless. Hours later, sensors detect rapid changes in the surrounding environment. The gas bonds with oxygen in unexpected ways, altering the air composition. Before the reaction can be stopped, it spreads through the ventilation system. The lab is sealed, but questions remain about whether anything escaped. Even if the sample contains no living organisms, chemical contamination poses a risk. Exotic compounds could be toxic, corrosive, or highly unstable. A small piece of material could ignite or explode if mishandled. If such a reaction occurred during transport, it might destroy not only the sample, but also the spacecraft carrying it. Worse, fragments could scatter across a wide area, spreading the very hazard we sought to contain. To prevent these outcomes, strict protocols are required. Spacecraft must be sterilized before launch to reduce forward contamination. Sample return capsules must be built to the highest standards of containment with multiple layers of protection. Laboratories handling the material must operate under extreme isolation, similar to facilities used for studying dangerous pathogens on Earth. Even with these measures, the risk cannot be reduced to zero. Imagine a team preparing for a mission to this mysterious object. Engineers design robotic arms and drills using materials that can withstand sterilization. Technicians wear full protective gear while assembling the spacecraft in clean rooms. Despite these efforts, a single human sneeze or a particle of dust could slip through. Once the spacecraft leaves Earth, that contaminant travels with it, waiting to land on the object's surface. Later, when samples are collected, no one can be sure which compounds came from space and which came from us. The same problem exists in reverse. Suppose the return capsule lands safely in a remote desert. Recovery teams approach cautiously, using sealed vehicles and suits. They transport the capsule to a laboratory built deep underground. Inside, robotic systems handle the material without direct human contact. Scientists examine it behind layers of glass and steel. Every step follows strict procedure. Yet even in this controlled environment, human error can occur. A misread sensor, a faulty seal, or a delayed alarm could allow contaminants to escape. Political and social pressures add to the complexity. Some groups might demand immediate access to the samples, arguing that delays slow progress. Others might insist on destroying the material entirely to eliminate risk. Governments must balance scientific curiosity with public safety. If an incident occurs, trust could collapse. People might fear space exploration, leading to conflict over future missions. Consider a situation where a strange illness appears near the recovery site. Local hospitals report unusual symptoms, and rumors spread quickly. Even if the illness has nothing to do with the sample, public perception links the two. Panic grows, fueled by media coverage and speculation. Authorities face the challenge of proving a negative, that the space material is not to blame. Meanwhile, scientific work is disrupted as containment efforts intensify. The reverse is also true. If humans contaminate the object first, future discoveries may always be questioned. A single false result caused by Earth microbes could cast doubt on decades of research. Scientists would argue endlessly about whether they had ever truly detected alien life. This uncertainty could stall progress and erode public confidence in space science. In both directions, contamination risks are tied to our lack of experience. We have never encountered a completely foreign ecosystem or chemistry. Our tools and models are built for Earth-based life and materials. An alien sample might not behave in any way we expect. It could dissolve in water, react to light, or change when exposed to heat. Without knowing these properties in advance, even basic handling becomes dangerous. Imagine holding a vial of dust that could either reveal profound secrets or unleash unknown hazards. That is the challenge facing scientists and engineers as they plan to intercept objects from beyond our world. Every action must balance the thirst for knowledge with the responsibility to protect both the object's environment and our own. In space exploration, curiosity and caution are forever linked by the unseen risks that travel with every fragment we touch. The object drifts silently through the dark, traveling along a path shaped by the pull of gravity. From Earth, it looks like any other comet or asteroid. Telescopes track its motion and generate predictions for its future positions. At first, the tracking is easy and the object appears harmless. But the closer it gets, the more urgent the work becomes. The time to study it is short, and every delay matters. Once it moves past a certain point, it will vanish back into deep space, and no one knows when another opportunity will come. When a new object enters our solar system, there is a brief window to observe it closely. The window begins the moment it becomes bright enough for our instruments to detect. It ends when it fades again into the darkness, or travels too far for a spacecraft to reach. These windows are always temporary. If clouds block ground-based telescopes for a week, or if funding delays slow the launch of a probe, that window can close forever. Missing it means losing not just the object, but also the data that only it can provide. Imagine a comet discovered at the edge of the solar system. At first, it is little more than a faint speck of light in a telescope's view. Scientists scramble to gather early measurements. These first readings help predict its path and speed. If those measurements are wrong, the predictions will be wrong too. A miscalculation at this stage can waste valuable time. By the time the error is noticed, it may be too late to correct course. The object will continue moving while our plans lag behind. Consider a mission designed to intercept the object. Spacecraft take years to build and months to travel. The launch must happen at a precise moment to match the object's trajectory. If the launch is delayed even by a few days, the spacecraft may miss its target completely. Engineers can try to adjust by using extra fuel, but fuel is limited. Too much adjustment may leave the spacecraft unable to complete its return trip or perform key maneuvers. A single missed deadline can collapse the entire mission. The same challenge applies to observation from Earth. Some objects move close to the Sun as they approach, making them difficult or impossible to see with optical telescopes. Others pass near the Earth for only a few days before retreating again. If clouds cover the sky during that critical moment, the opportunity is gone. Imagine a team waiting for a window to open. They have spent months preparing instruments, calibrating sensors, and training staff. The object will pass overhead for a single night. Data collected during those hours will determine whether their theories hold true. Then a sudden storm rolls in, blocking the view. The team watches helplessly as their chance slips away. They cannot reschedule. The object will not wait for better conditions. Even when conditions are perfect, the sheer speed of these objects creates limits. A comet traveling at tens of kilometers per second can cross millions of kilometers in a matter of days. Instruments must be ready to capture data at exactly the right moment. Cameras need to be aimed precisely, and sensors must be triggered at just the right time. A delay of even a few seconds can mean missing a key event, like the first burst of gas as the comet heats up near the Sun. Once missed, that moment can never be repeated. This time pressure affects decisions on what to study. Scientists may want to gather a wide range of data: chemical composition, surface images, thermal readings, and more. But there is rarely enough time to collect everything. Choosing one measurement often means sacrificing another. These choices can shape our understanding for decades. If the wrong data is chosen, entire fields of study might develop around incomplete or misleading information. Consider a scenario in which the object turns out to be unlike anything we have seen before. Early readings suggest unusual materials or strange behavior. By the time this is noticed, the window for sending a probe has nearly closed. Launch teams rush to adapt an existing spacecraft, cutting corners to meet the deadline. The probe reaches the object, but some instruments fail because they were not tested for these new conditions. The mission returns incomplete data, leaving more questions than answers. The chance to design proper equipment will not come again for many years. The window can also close due to the object itself. Some comets break apart as they approach the Sun. Others erupt with sudden jets of gas that alter their paths. A fragmenting object may scatter into pieces too small to track. Once this happens, missions must be cancelled or reworked entirely. If the breakup occurs earlier than expected, it can wipe out years of planning overnight. In addition to physical challenges, human factors play a role. Different countries may disagree on how to handle a rare object. Some may want to study it closely, while others view it as a potential hazard. Political debates can delay decisions until the window is nearly gone. By the time agreements are reached, it may be too late to act. Imagine a situation where one nation builds a probe and another controls the only available launch vehicle. Both sides must cooperate. A dispute over costs or data sharing stalls negotiations, the launch date approaches, and neither side backs down. Finally, the window passes. The object moves beyond reach, and the mission is abandoned. Years later, scientists still debate what could have been learned if they had acted sooner. Even when everything goes smoothly, the time constraints create stress for those involved. Engineers work long hours to prepare equipment. Astronomers stay awake night after night watching the sky. Mistakes are more likely under this pressure. A mislabeled file or a missed command could ruin an entire observation sequence. In some cases, the error is not discovered until long after the object has moved on. Imagine a final moment as the object speeds away. Telescopes capture the last faint images. Data streams slow and then stop. Scientists review what they have collected, knowing there will be no second chance. Questions remain unanswered. Some theories are confirmed, others disproven, but much remains unknown. The object continues into the darkness, carrying its secrets with it. The limits of these windows remind us how fragile our opportunities are. Space is vast, and most of it is beyond our reach. When an object passes close enough to study, it is like a brief door opening. If we hesitate or falter, that door closes and we are left staring into the dark, wondering what might have been discovered if we had acted in time. A distant object appears in the outer solar system, moving slowly against the backdrop of stars. At first, it seems unremarkable, a comet like many others we have tracked before. Observatories log its position and speed. Early measurements fit the expected patterns, so it is classified and filed away. But as more data comes in, small details begin to stand out. The shape is unusual. Its rotation does not match typical models. The gases escaping from its surface are unlike anything recorded in previous missions. At first, these irregularities are dismissed as errors. Instruments are recalibrated, readings checked and rechecked. When the results remain the same, questions grow. If the data is accurate, then the object is not behaving like a normal comet. Scientists try to fit the information into existing theories. Perhaps the object formed in a colder region of space, or its surface was altered by past collisions. But each new observation makes these explanations less convincing. The standard models no longer work. This moment when reality no longer matches our understanding is the beginning of paradigm shock. It happens when an event forces us to question the foundations of what we believe to be true. For planetary science, this could mean rethinking how comets form, how the solar system evolved, or even how planets like Earth came to be. Imagine a mission sent to study the object up close. The spacecraft approaches and begins sending back images instead of a loose, icy surface. It finds sharp, geometric structures buried beneath layers of dust. The composition is completely alien materials that should not form naturally under known conditions. Instruments detect isotopes that have never been seen before, ones that suggest a process outside the range of natural planetary chemistry. These discoveries do not just add detail to our theories, they contradict them entirely. Scientists try to explain the findings without overturning everything they know. Some propose rare natural processes that might account for the shapes and materials. Others argue the data must be flawed. Meetings are held, papers debated, and rival groups clash over interpretations. Slowly, the evidence piles up until denial is no longer possible. The object's behavior is not an anomaly. It is a direct challenge to our understanding of how the universe works. Consider the impact this would have on established models. For decades, planetary science has been built on certain assumptions that comets are relics of the early solar system, that their compositions reflect the materials present at the time of planet formation, and that their behavior follows predictable patterns. If even one of these assumptions is proven false, the ripple effects spread across many fields. Textbooks would need rewriting. Simulations of solar system evolution would need rebuilding. Previous conclusions about Earth's history, the origins of water, and the possibility of life elsewhere might no longer hold. This upheaval would not stay confined to laboratories and universities. Space agencies plan missions based on existing models. If those models collapse, years of planning could be rendered useless. A probe designed to study a comet may carry instruments optimized for substances that turn out not to exist. A sample return mission could collect material that behaves in ways no one expected, risking contamination or even destruction of the craft. Funding decisions would be thrown into question as priorities shift suddenly. Public reaction would add another layer of complexity. People are accustomed to thinking of science as stable and authoritative. When a discovery shows that our most basic ideas were wrong, trust can falter. Some might see the new data as exciting, a sign of progress. Others might interpret it as proof that scientists cannot be relied upon. The resulting debate could spill into politics, education, and even religion, with each group drawing its own conclusions about what the discovery means. Imagine a press conference announcing that the object's composition cannot be explained by natural processes. Reporters press for answers. Are we dealing with a sign of life? Evidence of an ancient civilization, a completely new kind of physics. The scientists at the podium hesitate, careful not to claim more than the data supports. Their uncertainty only fuels speculation. News outlets run dramatic headlines. Social media fills with theories and arguments. Governments issue statements urging calm while quietly holding private meetings to discuss the implications. The situation could grow even more unstable if the object shows active behavior. Suppose it changes direction in a way that cannot be explained by gravity or outgassing. Suppose it releases materials in timed bursts rather than random patterns. These actions would suggest deliberate control. At that point, the paradigm shock would deepen, moving beyond planetary science into the realm of existential questions. Humanity would have to confront the possibility that we are not alone, and that another intelligence has been present, unobserved, until now. Even without such dramatic signs, the practical effects of paradigm shock would be felt everywhere. Climate models rely on assumptions about the origins of Earth's atmosphere and oceans. If those assumptions are wrong, predictions for the future might need to be revised. The search for life on other planets depends on knowing what chemical markers indicate biological activity. If alien processes can produce those markers without life, entire strategies for detecting habitable worlds would need to change. Consider a concrete example. For decades, scientists have believed that water on Earth came primarily from comets. Missions have been designed to test this theory by measuring the ratio of hydrogen isotopes in cometary ice. If the object's measurements show a completely different ratio, one that cannot match either Earth or known comets, the entire theory collapses. Suddenly, the origin of Earth's oceans is a mystery again. Researchers must go back to the beginning, questioning every step of their reasoning. The emotional impact on the scientific community would be profound. Many researchers spend their entire careers building models and theories. To see those structures crumble can be deeply unsettling. Some will adapt quickly, eager to explore the new possibilities. Others will resist, clinging to old ideas even as evidence mounts against them. This tension can slow progress, creating years of debate and conflict before a new consensus emerges. Imagine the personal story of one scientist. She has spent 20 years studying comet formation. Her work is widely cited, and her models are considered standard in the field. When the new data arrives, she reviews it carefully, at first confident she will find a flaw. As the weeks pass, she realizes her life's work is wrong. She must choose between defending her reputation and embracing the unknown. This quiet, private struggle mirrors the larger upheaval happening across the scientific world. The shock is not just intellectual, it affects how humanity sees itself. For centuries, we've placed ourselves in a narrative of gradual discovery. Each new finding fits into a larger picture, filling gaps without overturning the whole. A truly disruptive discovery breaks that pattern. The universe may be far stranger than we have imagined. As the object moves away, carrying its mysteries with it, humanity is left to grapple with what was learned and what remains hidden. The data will be studied for decades, but the moment of first realization, the moment when old theories cracked and fell apart, will be remembered as the day the familiar world of planetary science ended and something entirely new began. An unusual object appears on the edge of the solar system. It moves in a way that seems natural at first, but new data shows odd details. Its shape is strange, and it reflects light differently than a typical comet or asteroid. The news spreads quickly. Scientists, the public, and governments all begin to speculate. Some think it is a fragment from another star system. Others whisper about the possibility of alien technology. Even without proof, the idea takes hold. It is an irresistible story, far more exciting than ordinary research. Funding agencies notice the surge of interest. Politicians see an opportunity to be part of something historic. Budgets are discussed, and plans shift almost overnight. Missions that were years in the making are delayed or cancelled, so that resources can be redirected towards studying the mysterious object. The argument is simple. If there is even a small chance of it being artificial, it must take priority over everything else. This kind of focus carries risks. Space science already operates under limited budgets. Money spent on one project often comes at the cost of another. When attention is drawn to a single dramatic target, other important work suffers. Planetary defense, for example, depends on constant surveillance of near-Earth objects. These programs track asteroids that could impact our planet, giving us warning and time to respond. If funding is cut to chase an extraordinary mystery, gaps appear in this safety net. An asteroid that could have been detected early might go unnoticed until it is too late. Imagine a small research group monitoring hazardous asteroids. Their work is routine and quiet, involving long nights of observation and careful calculations. They receive just enough funding to maintain their telescopes and pay their staff. When the strange object is discovered, a new committee forms to oversee research into it. The committee pulls funding from other programs, arguing that this discovery is a once-in-a-lifetime opportunity. The small group loses key staff members and is forced to reduce its operations. Months later, they miss detecting a dangerous asteroid because their equipment is offline. The asteroid passes close to Earth, and only sheer luck prevents disaster. The problem is not just about defense. Ordinary planetary science also depends on steady support. Missions to study Mars, Venus, and the moons of Jupiter and Saturn reveal vital information about the origins of our solar system. These missions are carefully planned over decades. If their funding is diverted, entire research paths can collapse. Scientists who have spent their careers preparing for specific missions may see their work vanish overnight. Younger researchers may leave the field entirely, taking their skills with them. This kind of disruption has long-term effects. Even if funding is restored later, the lost time cannot be recovered. A cancelled mission means a generation of data is never collected. The scientific record becomes incomplete, leaving gaps that may never be filled. These gaps affect not only basic research, but also practical understanding of space environments. For example, studying how radiation affects planetary surfaces helps engineers design better spacecraft. Without that knowledge, future missions become riskier and more expensive. The allure of alien technology is powerful because it promises something beyond ordinary science. People imagine breakthroughs that could solve major problems. Limitless energy, faster These visions inspire excitement and drive political support. But they are built on speculation. There may be nothing unusual about the object at all. It could turn out to be a lump of rock and ice with odd features, but no deeper mystery if that happens. The resources spent chasing it will have been wasted. and the program's sacrifice to fund it will be gone. Consider a space agency plans to launch a mission to study Jupiter's moon Europa, where evidence suggests a subsurface ocean that might harbor life. The mission is nearly ready. Then the strange object is discovered, and its potential as alien technology dominates headlines. Decision-makers decide to delay the Europa mission to free up funds for a rapid response mission to the object. Years pass while the new mission is designed, launched, and ultimately discovers nothing unusual. In that time, the Europa mission loses its launch window. The scientists involved retire or move on. A decade of preparation disappears, and humanity remains no closer to answering the question of life in our own solar system. The rush to study a mysterious object can also create competition between institutions. Universities, private companies, and government agencies may fight for control of the project. Each group wants to be the one that makes the discovery. This competition can lead to secrecy and poor coordination. Instead of sharing data, groups may withhold information to gain advantage. This slows progress and increases the risk of mistakes. It also creates duplication of effort, with multiple teams spending money to do the same work instead of collaborating efficiently. Public pressure adds to the problem. Once the idea of alien technology is in the news, it becomes difficult for leaders to act cautiously. Voters and taxpayers want answers. Politicians may push for faster timelines and more dramatic announcements, even if the science is not ready. Rushed missions are more likely to fail. If they do, the backlash can be severe, leading to further instability in funding. Media coverage plays a role in shaping these outcomes. A single image or leaked report can drive public opinion. If a blurry photo is interpreted as evidence of advanced technology, funding can surge overnight. When later analysis shows it was a natural formation, interest collapses just as quickly. This boom and bust cycle leaves scientists struggling to plan long-term projects in an environment of constant uncertainty. Imagine a scenario where a journalist obtains early data from the object showing unusual chemical readings. The story spreads globally, framed as proof of alien design. Governments respond by pouring billions into urgent missions. Months later, more careful analysis reveals that the readings were caused by contamination from the spacecraft's own instruments. By then, other programs have been cancelled, and budgets have been reshaped. The truth cannot undo the damage caused by decisions made in the heat of excitement. Even well-intentioned scientists can be caught up in this dynamic. The chance to work on a potentially historic discovery is tempting. Researchers may shift their focus to the object, leaving behind projects that seemed less glamorous. Graduate students may choose topics related to the mystery instead of other important areas of study. Over time, this creates an imbalance in the scientific community. Fields unrelated to the object shrink, while others become overcrowded and competitive. The danger lies in losing perspective. Space is vast and full of mysteries. Most discoveries are incremental, built on steady, careful work. When one object captures all attention, the broader mission of exploration is weakened. A balanced approach ensures that even if one path turns out to be a dead end, others continue to move forward. Without balance, a single mistake can set back an entire generation of science. The strange object at the edge of the solar system might hold secrets worth uncovering, but it could also be nothing more than a distraction. If we let its mystery reshape our priorities completely, we risk leaving ourselves vulnerable to hazards we can predict and challenges we already face. The excitement of the unknown must not blind us to the steady work that keeps our planet safe and our understanding of the universe growing. A faint object appears on the edge of the solar system. At first, it looks like a comet or asteroid. Telescopes record its path, and early calculations suggest it will pass harmlessly through. For a few weeks, it is just another discovery among many. Then a respected scientist publishes a paper suggesting that its motion is strange. The object is accelerating slightly, in a way gravity alone cannot explain. The paper raises the possibility that it might not be natural. It could, the author says, be a probe built by an advanced civilization. The idea spreads quickly. News outlets seize on the phrase alien spacecraft. Headlines appear around the world. Television shows and podcasts feature experts debating whether humanity has just encountered proof of life beyond Earth. Social media fills with theories and speculation. Within days, the object has gone from a minor curiosity to the center of global attention. Inside the scientific community, the reaction is mixed. Some researchers are intrigued by the data and want to investigate further. Others are skeptical and point to natural explanations like uneven outgassing or measurement errors. But the prestige of the scientist who proposed the alien theory carries weight. Younger scientists, eager to build careers, begin aligning their research with this exciting new idea. Grant committees notice the surge of public interest and start favoring proposals that mention the object and the possibility of technology. This is how groupthink begins. It starts with a respected figure setting the tone. Their interpretation becomes the default, even if it is based on limited evidence. Once the idea gains traction, people feel pressure to support it. Speaking out against it can be seen as being overly cautious or resistant to new ideas. Over time, dissenting voices grow quieter. Researchers who raise doubts find their work ignored or their funding cut. Imagine a small team studying comet dynamics. They publish a careful paper, showing that the object's unusual motion could be explained by hidden jets of gas on its surface. The data fits a natural model, though with some uncertainties. Their paper is reviewed politely but dismissed as unexciting. Another team publishes a more speculative paper suggesting deliberate maneuvers by a machine. That paper is featured in major journals and quoted in news reports. The natural explanation is lost in the noise. The pressure to conform does not have to be direct. It works through subtle cues. At conferences, panel discussions focus on the alien theory. Questions from the audience assume it is correct. Scientists who disagree feel isolated. They may stop raising objections simply to avoid conflict. Even the language used in official reports shifts over time. Words like anomaly and engineered replace more neutral terms. This creates a feedback loop, where the dominant theory shapes how data is interpreted, which in turn reinforces the theory. Consider how this plays out in practical terms. A mission is planned to intercept the object. Engineers must decide what instruments to include. Under normal circumstances, they would build tools to study ice, rock, and gas. But now, with the alien theory in play, there is pressure to include sensors that could detect metal structures or artificial signals. Limited space on the spacecraft forces trade-offs. Some traditional instruments are left out. If the object turns out to be natural, the mission will lack the tools to study it properly. Funding decisions follow a similar pattern. Agencies shift resources toward projects linked to the alien hypothesis. Proposals that do not mention it are delayed or rejected. This creates an incentive for scientists to frame their work in sensational terms, even if the actual data does not support it. Over time, entire research programs may drift away from balanced inquiry. The public plays a role as well. Once the idea of alien technology is out in the open, it shapes expectations. Journalists want dramatic stories, not cautious. Politicians see opportunities to align themselves with bold discoveries. A scientist who goes on television to say, "We don't know yet," sounds less compelling than one who confidently declares, "This could be proof of extraterrestrial intelligence." This dynamic rewards certainty over caution, even when certainty is not justified. Imagine a press conference about new data from the object. A conservative scientist carefully explains that the findings are consistent with both natural and artificial origins. Another scientist, more willing to speculate, announces that the data strongly suggests alien design. The second statement makes headlines worldwide. The first is forgotten. Future funding goes to the team that promised a breakthrough, not the one that urged patience. Over time, the alien theory becomes woven into the way the object is studied. Instruments are tuned to look for artificial patterns. Data that does not fit the narrative is dismissed as noise or error. This creates blind spots. Important natural phenomena may be overlooked because they do not fit the expected storyline. Entire lines of inquiry may wither away, leaving gaps in our understanding of comets, asteroids, and the solar system as a whole. This dynamic has occurred before in other fields. In archaeology, early theories about ancient civilizations shaped how ruins were interpreted. Artifacts that did not fit were ignored or misclassified. In medicine once, popular theories about disease delayed the discovery of germs, because researchers saw only what they expected to see. Science is vulnerable to these patterns because humans are vulnerable to them. Prestige, reputation, and career incentives can distort even the most rigorous disciplines. Imagine a young graduate student working on data from the object. She notices a pattern that suggests a natural process no one has discussed yet. When she brings it up to her advisor, he warns her to be careful. Publishing such a result could be seen as challenging the dominant theory. If she insists on pursuing it, her future funding might be at risk. Faced with this pressure, she sets the data aside and works on a project more in line with current trends. A potential discovery is lost, not because it was wrong, but because it was inconvenient. As the object moves closer to Earth, the stakes grow higher, missions are launched, policies debated, and public attention intensifies. The weight of expectation becomes enormous. At this point, even if new data contradicts the alien theory, reversing course becomes difficult. Too many careers, budgets, and reputations are tied to it. Acknowledging error would mean admitting that years of work were based on a false assumption. The most dangerous outcome is not that the object turns out to be natural. The danger is that, in chasing one extraordinary idea, other possibilities are ignored. If the object hides a more subtle threat, like a chemical hazard or a collision risk, it might go unnoticed until it is too late. Groupthink narrows vision. It creates a tunnel in which all data is interpreted through a single lens. When that lens is wrong, the entire effort is misdirected. By the time the object finally passes beyond reach, the truth may still be uncertain. Some will cling to the alien theory. Others will argue for natural explanations. The real damage will be in the lost opportunities. The data never gathered, the questions never asked, and the voices never heard, because they did not fit the dominant narrative. Science thrives on doubt and diversity of thought. When those are replaced by a rush toward a single sensational idea, understanding gives way to belief, and progress slows in ways that cannot be easily repaired. The object appears first as a faint dot of light in a wide-field survey image. At the edge of detection, it looks like any other distant body. Astronomers collect a few points of data and begin plotting its movement. In the early days, the information is sparse but clear. The object is moving fast, and it is on a trajectory that will bring it close to Earth. Telescopes around the world turn toward it, eager to gather more details. As more instruments come online, the flow of data increases. Within days, gigabytes of readings are pouring in from optical telescopes, radar arrays, spectrographs, and infrared sensors. The goal is to create a complete picture of what the object is and where it is going. The flood of data soon becomes overwhelming. Each instrument measures different things using different methods. A ground-based telescope reports a certain shape and brightness. A space telescope sees something slightly different. Radar produces conflicting results about its size. Even small discrepancies can create. Analysts must decide whether the differences are due to real changes in the object, or just noise in the measurements. Noise is always present. Space is full of interference from cosmic rays, solar activity, and background radiation. Even the best instruments pick up stray signals. A tiny error in calibration can shift results enough to matter. One telescope might record a bright flare that appears to come from the object. Another, observing at the same time, sees nothing. Was it a real event, or just a glitch? Scientists debate, but without clear evidence, the question remains unresolved. As the object approaches, the pressure to interpret the data grows. Predictions about its path and behavior depend on accurate numbers. But when the data is messy, those predictions become unstable. A single bad reading can ripple through the models, producing wildly different outcomes. Some projections might show a safe pass at a great distance. Others might predict a near miss, or even an impact. Decision makers must act while still unsure which model is correct. Imagine a control room filled with screens. Teams from different countries are feeding their measurements into a shared network. One group reports a sudden change in velocity. Another group sees no change at all. The discrepancy sparks arguments. Was the object affected by outgassing? Or did one team's radar misread the signal? There is no easy way to know. Every hour spent debating is an hour lost as the object continues to move closer. The problem grows worse when signals are ambiguous. Spectral analysis might show chemical traces that could mean many different things. A certain reading could indicate frozen methane, unusual minerals, or even artificial alloys. Without context, the data cannot be interpreted with certainty. Teams run simulations using different assumptions, but each produces a different answer. The result is a cloud of possibilities rather than a clear conclusion. Consider how this affects mission planning. If the object is mostly ice, a probe can approach safely at close range. If it contains volatile chemicals, a close approach could be dangerous. Engineers must design equipment without knowing which scenario is true. They build extra safety systems, which add weight and complexity. Some instruments are included, others left out, based on incomplete information. The final spacecraft is a compromise, shaped as much by guesswork as by science. The sheer volume of data also creates logistical problems. Petabytes of information arrive from different sensors each day. Storage systems strain to keep up. Automated filters try to sort the data, but they can misclassify important signals as background noise. Human analysts must review the flagged data manually, a slow and tiring process. Mistakes are inevitable. A key reading might be overlooked because it was buried in thousands of false positives. Imagine a spectrograph detecting a faint repeating signal. The pattern is unusual and might indicate something remarkable. But at the same time, dozens of other anomalies are being logged. A tired analyst working late at night might dismiss it as an artifact without looking closely. Weeks later, when someone finally reviews it, the signal is gone. By then, the object has moved on, and the chance to confirm it is lost. Conflicting data can also fuel disagreements between teams. One group may interpret a blurry image as evidence of a smooth surface, while another sees hints of sharp structures. Each team publishes its findings, and the public hears wildly different stories. News outlets report both interpretations without context, creating confusion and speculation. The debate distracts from urgent tasks like tracking the object's exact position, as more countries and organizations join the effort. The problem compounds. Different instruments have different levels of precision. Some are decades old, while others are state-of-the-art. Their readings do not always align. Political considerations creep in as well. A nation might withhold certain data or emphasize results that support its own narrative. Scientists must navigate not only technical uncertainty, but also human agendas. The noise to signal ratio worsens as the object draws closer. When it enters regions of space crowded with satellites and debris, background interference spikes. False echoes appear on radar. Optical telescopes capture flashes of light caused by reflections off unrelated objects. Sorting through this clutter becomes nearly impossible. Analysts must work under the assumption that some of what they see is real and some is not, without always knowing which is which. Consider a scenario in which a single misinterpreted signal triggers a chain reaction. A radar station picks up what looks like a small fragment breaking away from the object. Other stations cannot confirm it, but the report spreads quickly. Plans are made to track this supposed fragment. Resources are diverted and other tasks are delayed. Days later, it becomes clear there was no fragment at all. The reading was caused by a passing satellite. By then, valuable time has been wasted. The human element adds further complications. Scientists are under intense pressure to provide answers. Governments, the media, and the public demand clarity. In this environment, people may overstate their confidence. A researcher might present a preliminary finding as certain to secure funding or influence decisions. Later, when the result is proven wrong, trust erodes. Skeptics grow louder, and every new piece of data is questioned, even when it is accurate. Ambiguous signals can also fuel wild theories. When evidence is unclear, imagination fills the gaps. Some will claim the object is entirely natural, others that it is artificial. Each interpretation finds support in some corner of the messy data. These competing narratives distract from the careful, patient work needed to resolve the truth. The last streams of data come in, chaotic and incomplete. Scientists piece together what they can, like archaeologists assembling a shattered mosaic. Some questions are answered, but many remain open in the end. The record is patchy. Key events were missed or misunderstood. Years of analysis will follow, but the picture will always be incomplete. The challenge of data overload is not just technical. It is about limits. Limits of our instruments, our systems, and our ability to interpret a flood of information under pressure. In the vastness of space, clarity is rare, even with our best efforts. What we see is often a mixture of truth and noise, and separating one from the other can be as difficult as the mysteries we hope to solve. A faint object is first spotted in the night sky by a small group of astronomers. At the start, it is just a distant point of light, moving slowly against the background of stars. They track it, measure its path, and share the data with other observatories. For weeks, the work is quiet and methodical. Early reports are cautious, describing it as a comet or asteroid passing through the solar system. Then, a strange detail emerges. The object's speed or brightness changes in ways that do not fit simple models. A respected scientist mentions in an interview that its behavior is unusual and might deserve special attention. That single remark is enough to spark interest far beyond the scientific community. A news outlet runs a headline calling it a mysterious visitor from deep space. Other outlets copy the story, each adding their own spin within days. The object has moved from academic journals to the front page of every major site and newspaper. The story spreads across social media. Some posts claim it is a harmless rock, others declare it must be an alien spacecraft. Photos and videos, real and fake, begin circulating. People argue over every pixel and every rumor. The public is not trained to interpret orbital data or spectral readings. Most people rely on second-hand explanations. When those explanations are filtered through sensational headlines, the meaning changes. A careful scientific statement, like "we cannot rule out artificial origin," becomes scientists confirm alien probe. Fear and excitement grow together, feeding on uncertainty. The more ambiguous the real data, the more space there is for imagination to take over. Governments and agencies face intense pressure to respond. Journalists demand answers at press conferences. Politicians ask for briefings they cannot fully understand. A single misinterpreted sentence can set off a storm of reactions. If an official says, "We are still gathering information," it may be taken as proof they are hiding the truth. Silence is treated as conspiracy. Clear communication becomes almost impossible once the narrative takes on a life of its own. Imagine a televised announcement about the object. The lead scientist carefully explains that current observations suggest no danger, but continued monitoring is needed. The scientist's tone is calm and precise. A few minutes later, a news site posts a headline reading, "Officials say threat cannot be ruled out." Social media amplifies this version, stripped of context. Within hours, people across the world believe the government is hiding a looming disaster. Panic begins in small ways. Grocery stores see sudden spikes in purchases of bottled water and canned food. Families cancel travel plans, stock markets dip as investors react to uncertainty. Then the fear spreads further. Talk shows invite self-proclaimed experts who claim inside knowledge. Conspiracy theories emerge, arguing that the object has been known for years and deliberately kept secret. Every gap in official information becomes evidence for these theories. Hype can be just as dangerous as fear. Some people view the object as proof of a coming golden age. They believe alien technology will solve Earth's problems overnight. This belief drives irrational behavior. Investors pour money into companies claiming to work on reverse engineering alien tech. Politicians promise to lead humanity into a new era, using the mystery to rally support. The focus shifts from real science to speculation and fantasy. The cycle between fear and hype grows faster with every news update. A small technical change in the object's observed path might mean nothing to astronomers. To the public, it is headline material. Trajectory shift becomes incoming threat. Late night hosts joke about evacuation plans. Serious researchers find their voices drowned out by louder, more dramatic ones. Imagine a scenario where a spacecraft is launched to intercept the object. The mission is complex and delicate, requiring months of preparation. But to the public, it becomes a race against time, like a movie plot. News coverage frames it as a final defense against destruction. If the mission succeeds, it will be hailed as heroic. If it fails, no matter the reason, it will be seen as proof that leaders are incompetent or hiding something worse. This all or nothing framing leaves no room for nuance or gradual discovery. Social media accelerates the problem. A single viral post can reach millions of people in minutes. If someone uploads a blurry photo claiming to show the object changing shape, it spreads faster than any official correction. Algorithms prioritize engagement, not accuracy. Emotional posts, especially those filled with fear or anger, rise to the top. This creates a feedback loop. The more frightening or exciting the claim, the more people see it and share it. In this environment, false information outpaces truth. Fact checking becomes a losing battle. By the time an official statement is released, the public has already moved on to the next rumor. Even if the statement is clear and accurate, many will dismiss it as propaganda. The more chaotic the information flow, the easier it becomes for bad actors to exploit it. Some groups may deliberately spread falsehoods to advance their own agendas. A hostile nation might circulate fake data to cause unrest in rival countries. Extremist groups could claim the object is a sign of divine judgment, using it to recruit followers. Opportunists might sell fake survival gear or miracle solutions, profiting from the fear. Each of these actions deepens the confusion and makes coordinated response harder. Governments may feel forced to take visible action, even when there is no clear threat. Military forces might be placed on alert. Space agencies could rush missions before they are fully tested. These decisions are made not because they are scientifically sound, but because leaders fear the political cost of appearing passive. A single accident, a rocket explosion, a misinterpreted radar signal could escalate into crisis. Imagine a false alarm triggered by a routine satellite malfunction. In normal times, it would be a minor technical issue, but in the charged atmosphere created by hype, it could be misread as proof that the object has taken action. Media outlets would report it instantly. Social media would amplify it. Governments might respond militarily before realizing there was never a real threat. Even after the object passes by harmlessly, the effects of panic can linger. Trust in institutions may be permanently damaged. People who believed in dramatic theories will not easily accept mundane explanations. Every future discovery will be filtered through the lens of past hysteria. Scientists will face skepticism and hostility, no matter what they say. Consider the personal toll on those at the center of the storm. Astronomers who made the original discovery may face harassment and threats. Engineers working on missions might be accused of lying or covering up evidence. Public officials may find their words twisted until they bear no resemblance to what was actually said. Over time, this constant pressure erodes morale and makes it harder for experts to do their jobs. The object itself might be a simple comet, an inert rock following a natural path, but the reaction it triggers could be far more complex and dangerous than the object itself. When fear and hope collide in the public sphere, rational decisions become difficult. The real challenge is not only to study what is out there in space, but also to manage what happens here on Earth. When the sky brings us mysteries we cannot yet explain. A small team of astronomers first notices the object, a faint speck moving against the backdrop of stars. At first, they share the data freely, as is common practice. Other observatories confirm the sighting and add their own measurements. For a brief moment, the discovery feels like a shared triumph. Scientists from different countries work together, combining information to refine the object's path. But as the data grows stranger, so do the stakes. Its motion is unusual, and its composition is unlike anything seen before. Governments take notice. What began as open collaboration soon shifts into a contest over who controls the information. The first signs of tension are subtle. A national space agency delays releasing updates, saying they need to verify their results. Another country suddenly stops sharing telescope time with international partners. Official statements grow vague, filled with technical terms that reveal little behind the scenes. Intelligence agencies begin classifying certain reports. Scientists who were once colleagues now receive orders to limit what they say, even to trusted collaborators. Each nation has its own reasons. Some fear that the object could contain technology. If there is even a small chance of that, they want to be the first to study it. Control over potential alien technology could mean economic and military advantage. Others worry about public reaction. Releasing raw data might fuel panic or conspiracy theories. Leaders decide it is safer to keep information hidden until they fully understand it. But secrecy breeds suspicion. When one country withholds data, others assume the worst. Imagine a scenario where two rival nations track the object as it approaches Earth. Their scientists have similar readings, but each side interprets them differently. One group believes the object will pass harmlessly by. The other thinks it might release smaller fragments into orbit. Neither side trusts the other enough to share their methods. In meetings at the United Nations, both make confident statements but refuse to show their evidence. The result is deadlock. No one knows which assessment is correct, yet no one will admit uncertainty. As the object draws closer, the competition escalates. spacecraft are proposed to intercept it. Building and launching such missions requires enormous resources, so only a few nations can act quickly. Each wants to be the first to reach the object, not just for scientific discovery, but also to control what is found. Agreements about data sharing break down. Joint missions are scrapped. Instead, separate teams work in secret, duplicating effort and burning through funds. This competition extends to the ground as well. Telescopes in neutral countries face sudden pressure. A private observatory might receive generous funding from one government, followed by quiet demands to restrict access. Another country might threaten to cut off trade or partnerships unless certain images are withheld. Even individual scientists can become targets. A researcher with unique expertise may be offered a lucrative position abroad, not just for their skills, but for the data they can bring with them. The tension spills into public view when inconsistent reports reach the media. One government claims the object is inert and harmless. Another hints at strange activity, suggesting deliberate movement. News outlets broadcast both claims without context, fueling confusion. Citizens begin to suspect that their leaders are hiding the truth. Protests erupt, demanding transparency. Governments respond with carefully crafted statements that reveal nothing, further deepening mistrust. Imagine a press conference where officials are asked directly whether the object is natural or artificial. The spokesperson dodges the question, citing national security. Within hours, social media is filled with theories. Some people believe an alien ship has already been captured. Others accuse rival nations of staging the entire event for political gain. The lack of clear information allows rumors to flourish unchecked scientific collaboration. Once a strength becomes a casualty of this environment. International teams that spent decades working together on space missions now face travel restrictions and visa denials. Shared databases go offline. Even neutral organizations, like the International Astronomical Union, struggle to coordinate because member nations no longer trust each other. Data that once flowed freely now moves through secure channels. If it moves at all, consider a mission already in flight. Its instruments are designed to send back real-time readings of the object's composition. The data is supposed to be shared instantly with researchers worldwide. But as the political climate worsens, access is restricted. Only a small group of officials can see the unfiltered data. Other scientists receive summaries that have been edited to remove sensitive details. They begin to notice gaps and inconsistencies. Some suspect deliberate manipulation. The competition also affects planetary defense. If the object poses even a slight collision risk, early detection is crucial. Yet no country wants to reveal how accurate its tracking systems are. Revealing precise data could expose the capabilities of military satellites. As a result, warnings are delayed. By the time information is released, the window to act has narrowed dangerously. A problem that could have been solved through open cooperation instead becomes a crisis. Economic factors add another layer. Companies with ties to space exploration see opportunities in secrecy. A private contractor might develop specialized equipment for studying the object. Governments eager to gain an edge grant exclusive contracts without competitive bidding. Patents are filed under classified programs. Rival companies, shut out of the process, lobby their own governments to retaliate. Commercial disputes merge with national rivalries, creating a tangled web of competing interests. Imagine a sudden breakthrough. One nation's probe sends back images showing structures on the object's surface that appear artificial. The images are immediately classified. Officials debate how to proceed. If they release the pictures, they risk global panic and lose their exclusive advantage. If they withhold them, other nations might detect signs of secrecy and respond aggressively. The decision is made to release only a single, heavily edited image. Analysts worldwide scrutinize it, searching for clues about what has been hidden. This partial disclosure satisfies no one. Diplomatic channels strain under the pressure. Emergency meetings are held, but progress is slow. Each side suspects the others of hiding critical information. Allies quarrel. Old rivalries resurface. Even cooperative agreements unrelated to space, such as trade deals or climate initiatives, begin to falter. The mystery of the object becomes a symbol of broader distrust. Meanwhile, the scientists themselves are caught in the middle. Many entered the field to expand knowledge and share discoveries. Now they find their work used as political currency. Some are silenced by gag orders. Others speak out and face professional ruin. A few choose to leak data anonymously, risking imprisonment. These leaks create new problems as partial information circulates without context, fueling both hope and fear. As the object passes near Earth, the world watches in confusion. Different nations broadcast different interpretations. Some say it is a simple rock. Others claim it is evidence of advanced life. No one knows which version is true. The real danger is not just the object itself, but the way secrecy and competition have fractured the ability to respond. By the time the truth emerges, the relationships that once supported global science may be damaged beyond repair. The object appears first as a distant point of light. At the start, no one sees it as a threat. Astronomers track its path and predict a harmless flyby. As more data comes in, the picture changes. Its trajectory is unusual, and small variations in its speed are hard to explain. Some models suggest it will pass at a safe distance, while others show a potential near miss. With each new measurement, the uncertainty grows. By the time it becomes clear that the object deserves serious attention, the clock is already ticking. Governments meet to discuss options. Space agencies and military planners bring their models and proposals, but they quickly realize how little preparation exists for an event like this. There are plans for known threats like asteroids, but those plans assume predictable behavior and long warning times. This object is different. It is moving faster than expected and may not be entirely natural. If its course changes even slightly, the impact zone could shift by thousands of miles. No one is certain what it is made of or how it might behave as it approaches. Without reliable information, response planning becomes guesswork. Imagine a scenario where the object is fragile, like a loose cluster of ice and dust. A deflection attempt using explosives could simply break it apart, creating multiple hazardous fragments instead of one. If it is solid metal, the same strategy might fail completely, barely altering its path. With no clear data, planners must prepare for both extremes at once, stretching resources thin and delaying action. Time is the greatest enemy building, and launching a mission to intercept the object takes months or years. Even if a spacecraft is ready, it must be launched at a precise moment to match the object's speed and trajectory. A small delay can mean total failure. If the warning comes late, there may be no realistic way to reach it before it passes too close to Earth. The only remaining options would involve ground-based measures, which are even less certain. Consider the challenge of international coordination. The object's path crosses multiple national territories. If there is even a small chance of impact, dozens of countries need to cooperate on evacuation plans, communication strategies, and defensive actions, but such cooperation does not happen instantly. Questions of leadership and control arise. Who decides whether to attempt a deflection? Who takes responsibility if something goes wrong? In the absence of clear agreements, arguments consume precious time. Imagine two major powers with competing interests. One wants to launch a nuclear device to push the object off course. The other fears that such a launch could be mistaken for a weapon test or even an attack. Both sides hesitate, waiting for assurances that never come. While diplomats debate, the window for action closes. By the time they agree, the object is too close to intercept. Even simple measures like public warning systems are untested at this scale. If the risk is revealed too early, panic might spread before any plan is ready. If it is revealed too late, millions of people could be caught unprepared. Governments must strike a balance. But with incomplete data, every choice carries danger. A false alarm could destroy public trust for years. A delayed warning could cost countless lives. In many regions, emergency infrastructure is not designed for a space-related disaster. Evacuation routes may be limited. Hospitals may lack supplies to treat mass casualties. Communication networks might fail under sudden, heavy demand. These weaknesses only become clear when they are tested, and by then it may be far too late to fix them. Consider a coastal city directly in the projected path of a possible impact. Local officials begin quiet preparations, moving resources and updating emergency plans. But they are not given full information about the object's behavior, so they cannot know whether evacuation is truly necessary. If they evacuate too soon, they may face public backlash when the danger turns out to be minor. If they wait too long, traffic jams and confusion could trap thousands in harm's way. Military forces face similar challenges. Some defense systems could, in theory, be adapted to target incoming fragments. But these systems were designed for missiles, not massive objects traveling at tens of kilometers per second. Even if a strike is successful, it might only break the object apart, turning one problem into many. Training exercises have not prepared crews for this kind of mission. Decisions would have to be made under pressure, with little time to test or revise strategies. The lack of preparation extends to the scientific side as well. Scientists may not have enough instruments in place to gather critical data during the approach. They might be forced to rely on improvised setups, rushing to repurpose equipment meant for other uses. This can lead to errors or gaps in understanding. Without accurate data, planners are essentially blind, making guesses about composition, spin, and trajectory. These guesses shape defense plans, meaning a single wrong assumption can have cascading effects. Imagine that during the final days before closest approach, new data shows the object is much denser than anyone thought. The deflection mission already launched was built on the assumption of a lighter target. The force of impact is far too small to change its course meaningfully. There is no time to launch a second mission. Leaders must decide whether to attempt a risky ground-based response or focus entirely on evacuation. Either choice is made under extreme uncertainty, with lives at stake. Funding and political will also play roles. Many space defense proposals have been studied on paper for years, but never fully developed. Building such systems requires money, long-term planning, and public support. Without an immediate threat, these programs are often cut or delayed. When a real crisis arrives, there is no ready-to-use system waiting. Engineers and scientists must rush to assemble solutions under intense pressure, knowing they are improvising in ways that might fail. Even if the object proves to be harmless, the lack of preparation carries a cost. If drastic measures were taken unnecessarily, there could be economic damage and political fallout. Critics would accuse leaders of overreacting. Future warnings might be ignored because of past false alarms. This creates a dangerous cycle where caution is punished, making decisive action harder when it is truly needed. Imagine a near miss where the object passes safely by, but only after governments spent billions on emergency preparations. The public sees no visible danger and assumes the risk was exaggerated. Years later, when a new object is detected, officials hesitate to act, fearing backlash. That hesitation could turn a manageable threat into a disaster. The challenge is not just technical or scientific. It is also about decision, making under stress without clear plans. Every step becomes a negotiation. Different agencies may issue conflicting, local authorities may act independently, creating confusion and duplication of effort. Information spreads unevenly, leaving some regions well prepared, while others remain unaware. In a fast-moving crisis, this patchwork response can be worse than doing nothing at all. The approach of a mysterious object highlights how fragile our current systems are. In theory, we know what should be done. Track threats early, share data openly, develop defense technologies, and plan for worst-case scenarios. In practice, these steps are often delayed by politics, cost, and complacency. When a real event occurs, the gap between theory and readiness becomes painfully clear. By the time the world understands what is needed, there may be no time left to act. The discovery begins with a faint signal, a small dot of light moving through the sky. At first, no one thinks much of it. Objects like this are common, and they usually turn out to be simple comets or asteroids. Telescopes track its path, and early measurements seem routine. Then, new data arrives. Its motion is slightly unusual, its surface reflectivity odd, and it emits readings that do not fit cleanly with known patterns. Scientists begin to debate what they are seeing. Some suggest natural explanations like an irregular shape or unusual chemistry. Others point out that the data leaves room for another possibility. The object could be artificial, the product of a technology beyond Earth. This idea is not presented as certainty, only as one possible interpretation. But the moment the words alien probe appear in a report or interview, the discussion changes. Public reaction is immediate and intense. News outlets compete to run the most dramatic headlines. Social media explodes with theories and rumors. Politicians demand answers. In this storm of attention, fear grows faster than curiosity. People imagine worst-case scenarios: hostile machines, hidden surveillance, catastrophic attacks. Even though there is no evidence of danger, the possibility dominates public perception. Governments respond by framing the object primarily as a threat. Security agencies take control of key data streams. Access to certain instruments is restricted. Missions that were planned as purely scientific are rebranded as defensive or strategic. The language used in briefings shifts from exploration to containment. Questions about life beyond Earth are pushed aside in favor of discussions about risk and protection. This focus on danger has a chilling effect on the scientific community. Researchers know that suggesting an alien origin can be career-ending if it is seen as reckless. Those who once spoke openly about the search for life now choose their words carefully or avoid the topic entirely. Proposals to study signals or structures that might indicate intelligence are quietly shelved. Funding committees become reluctant to approve anything that could be criticized as speculative. Imagine a young scientist analyzing data from a deep space telescope. She sees a repeating pattern in the object's emissions, one that might indicate artificial design. In another era, she would publish her findings and invite others to test them. Now, she hesitates. She remembers what happened to a colleague who suggested a similar idea last year and was publicly mocked, then lost his research grant. The safest choice is to interpret the pattern as a natural process, even if the fit is poor. She writes her report in cautious language, and the possible discovery fades into obscurity. Over time, this caution becomes self-reinforcing. Because few researchers publish bold ideas, it appears there are none worth considering. Committees cite the lack of evidence as a reason to deny funding, which in turn discourages future work. A field that once thrived on imaginative hypotheses slowly narrows into safe, predictable studies. The search for life becomes a side project rather than a central goal. The consequences reach beyond academia. Space agencies that once planned missions to look for biosignatures or technological markers shift their priorities. Budgets are redirected toward defensive systems and monitoring programs. Instruments designed to detect faint traces of artificial activity are replaced with more conventional sensors. Even public communication changes. Officials downplay questions about extraterrestrial life to avoid inflaming fear or controversy. The very subject becomes taboo. Consider a mission already in development. It was built to land on a distant moon and search for chemical signs of life beneath the ice. After the discovery of the mysterious object, funding agencies review the mission's goals. They decide to repurpose it as a general survey of geological activity, cutting back on the life detection instruments. The stated reason is to reduce unnecessary speculation. When the mission launches, it collects valuable data, but the opportunity to answer the larger question, whether life exists beyond Earth, is lost. This shift also affects education and recruitment. Young scientists entering the field sense the boundaries of what is acceptable. They learn that certain questions cannot be asked openly if they want stable careers. As a result, fewer people specialize in astrobiology or technosignature research. Those who do must frame their work in indirect terms, avoiding language that might trigger scrutiny. Over a generation, the talent pool for these areas dwindles. The irony is stark. The initial discovery that sparked fear could have been a breakthrough in understanding humanity's place in the universe. Instead, it becomes a reason to close doors and narrow vision. The more energy spent on containment and secrecy, the less remains for exploration. The narrative of danger overshadows the possibility of discovery. Imagine a future meeting of international scientists and policymakers. A private group presents evidence that the object emitted structured signals during its closest approach. The evidence is compelling but incomplete. In a different climate, it would trigger new missions and open debate. Now, the officials respond with silence. They fear that acknowledging the signals would reignite public panic. Instead, they quietly file the report away and continue to speak of the object only as a natural body. The chance to investigate further slips away. Even when caution is justified, it can have unintended effects. By suppressing open discussion, authorities create a vacuum that rumors quickly fill. People outside official channels begin their own investigations. Amateur astronomers, private companies, and citizen scientists collect data and share it online. Without peer review or oversight, their interpretations vary wildly. Some see clear signs of alien engineering. Others insist the whole story is fabricated. This chaotic environment makes it even harder to separate truth from fiction. The cost of missed opportunities cannot be measured only in lost data. It also shapes humanity's collective imagination. For centuries, humans have looked to the stars and wondered if they are alone. That curiosity drives exploration, art, and philosophy. When fear replaces wonder, the narrative changes. Space becomes not a frontier to explore, but a threat to guard against. This shift influences public support for research, steering it away from bold questions towards safe, defensive goals. Consider a specific example. A decade before the discovery, an international project was proposed to build a powerful radio array capable of detecting faint signals from other star systems. The project struggled to gain funding, but after the mysterious object was detected, there was hope that interest would surge. Instead, the opposite happened. Governments decided that building a listening array might increase public anxiety or reveal sensitive information. The project was quietly cancelled. Its facilities were repurposed for surveillance of near-Earth space debris, a safer and more politically neutral task. The result is a paradox. In trying to protect humanity from a potential danger, we may prevent ourselves from learning whether that danger actually exists. The very tools needed to answer the most profound questions are set aside because they are considered too risky to use. The search for extraterrestrial intelligence stalls, not because the universe is silent, but because fear has made us deaf to its signals. In the years that follow, the object fades into the background of history. It is remembered as a strange encounter that caused a brief period of upheaval. Official reports describe it in purely natural terms. The possibility of technology is never mentioned. A few scientists continue to wonder in private, but they lack the resources to investigate. The data remains locked in secure archives, available only to a handful of officials. The sky remains full of mysteries, but the will to seek answers has weakened. Each new discovery is greeted first with caution, then with silence. Opportunities pass unnoticed because no one dares to look too closely. Humanity's understanding of the universe does not collapse in a dramatic moment. Instead, it narrows slowly until the search for life becomes not an active quest, but a forgotten dream buried beneath layers of fear and missed chances. The object comes from deep space, silent and unremarkable. To telescopes, it looks like a typical comet or asteroid, cold, dark, and ancient. It follows a predictable path, moving under the pull of gravity like countless other bodies we have tracked before. Scientists watch it for a while, collect data, and, once it passes, shift their focus to other projects. The object fades from public attention, another entry in a catalogue filled with numbers and orbital diagrams. But appearances can mislead. If the object carries systems designed to act slowly and quietly, they would not reveal themselves at first. These systems would wait, dormant, until the right moment. There would be no visible signal, no sudden maneuver to draw notice. The object would seem completely inert while it approaches, passes, and continues on its way. Only later, long after observers have stopped watching, would its true purpose unfold. Imagine a probe built to seed a planet with smaller devices. As it nears Earth, tiny units no larger than grains of sand could be released. These microprobes would disperse into the upper atmosphere or settle on remote surfaces like ice caps or ocean floors. Their size would make them invisible to most tracking systems. Even if a few were detected, they might be mistaken for natural debris or dust. Once deployed, they would remain inactive, conserving energy and avoiding detection. Over time, the microprobes would begin their work. Some might focus on surveillance, gathering information about radio signals, population movements, or environmental conditions. Others might specialize in replication, using local materials to build additional units. This process could be extremely slow, occurring over years or even decades. A handful of initial devices could grow into thousands without ever triggering alarms, because each step would be too subtle to stand out from background noise. Consider how difficult this would be to detect. Human technology is tuned to look for dramatic events, bright lights, strong signals, sudden changes. A system designed to act below those thresholds would blend seamlessly into the environment. A probe might transmit using frequencies that overlap with natural sources like lightning or solar activity. It might send data in patterns that resemble ordinary interference. Even if a signal was intercepted, analysts could dismiss it as random noise. The danger grows because the timeline is so extended. Traditional defense planning assumes threats will appear in clear, urgent ways. A missile on radar, a storm approaching, a cyber attack unfolding in minutes. A slow invasion does not fit this pattern. Years may pass with no obvious sign of danger. By the time enough evidence accumulates, the network of hidden systems could be deeply embedded. Removing it would require extraordinary effort, and the cost of doing nothing would already be high. Imagine a scenario decades after the initial encounter. Satellites begin to malfunction in unusual ways. At first, the failures seem unrelated. A weather satellite here, a communications relay there. engineers blame aging hardware or routine space debris. But as incidents increase, a few specialists notice patterns. The failures cluster in certain regions and occur in synchronized intervals. By then, thousands of devices might already be in orbit, operating silently, each one performing a small part of a larger plan. The same process could unfold on the ground. Tiny machines scattered across remote landscapes might study ecosystems, infrastructure, and even human behavior. They could gather intelligence for years, sending data back in ways too subtle to notice. A sudden burst of activity is not necessary. The goal would be to understand the target thoroughly before acting. When the time came to interfere, by disrupting communications, damaging resources, or influencing decision-making, the systems would already be in place, ready to execute their tasks. This approach offers strategic advantages. A sudden attack invites an immediate and coordinated response. A slow, hidden build-up avoids that risk. Humans are prone to overlooking gradual change. If the compromise happens in small steps, each one may seem too minor to address. Officials might dismiss early warnings as false alarms or exaggerations. Budgets might not be approved for countermeasures against a threat that cannot be clearly defined. Consider how this plays out politically. A scientist detects unusual readings in a remote area and reports them to a national agency. The agency investigates but finds nothing conclusive. With limited evidence, they decide not to issue a public warning. Months later, similar readings appear in another location. Again, the data is too weak to prove anything. Each time, the response is the same. Study quietly. Avoid alarm. Wait for more information. By the time the pattern is undeniable, years have passed and the systems have spread far beyond the initial sites. The psychological effect of such a threat is profound. People expect danger to announce itself clearly. When nothing dramatic happens, they assume there is nothing to fear. This makes it easy for leaders to downplay concerns, whether through genuine belief or deliberate choice. Those who raise alarms may be seen as paranoid or politically motivated. In this environment, denial becomes the default, giving the hidden systems even more time to grow. Imagine a hidden network that not only collects data but adapts over time. The microprobes might change form or behavior in response to human activity. If detection methods improve, the systems evolve to avoid them. If certain regions become heavily monitored, the devices shift to less protected areas. This slow adaptation mirrors biological evolution. Just as species change gradually to survive in new conditions, the network could refine itself to remain invisible. The final phase of such a strategy might not involve open conflict at all. Once the network is large enough, it could influence events subtly but decisively. Communications might fail during critical negotiations. Power grids could experience unexplained outages at key moments. Financial systems could be disrupted in ways that seem like random errors. Each event would appear isolated, caused by technical glitches or natural disasters. The true connection between them would remain hidden. Consider a global crisis sparked by such interference. Governments scramble to respond to what they believe are unrelated problems. Resources are divided and misallocated. Trust between nations erodes as each suspects the others of sabotage. In this confusion, the hidden network continues to operate smoothly, achieving its goals without ever revealing its existence. Even if the threat is eventually discovered, response would be complex and dangerous. Destroying the network might require disabling parts of Earth's own infrastructure. Some systems could be so deeply integrated that removing them would cause more harm than leaving them in place. The line between defense and self-destruction would blur. The greatest challenge lies in early detection. By the time physical evidence is found, a fragment of alien material, a device retrieved from the ocean floor. The network might already be vast. Reverse, engineering the technology could take years. And during that time, the remaining devices would continue their work. Human efforts to build countermeasures would always lag behind. Imagine a small lab examining the first recovered probe. Scientists marvel at its complexity and efficiency. They realize it has been operating for decades without notice, powered by mechanisms they do not fully understand. As they study it, they begin to see hints of larger structures and hidden connections. But outside the lab, more probes continue to move quietly, unseen, completing tasks that remain mysterious. The slow invasion is not a dramatic arrival with flashing lights and open conflict. It is a quiet presence that grows unnoticed, like a shadow lengthening at sunset. By the time anyone realizes it is there, it has already become part of the environment, embedded so deeply that removing it might no longer be possible. In this way, a single object passing through the solar system could plant seeds of change that unfold over generations, reshaping the world without a single overt act of war. The object arrives without warning. It drifts into the solar system like countless comets and asteroids before it. Telescopes track its path, note its speed, and calculate its orbit. At first, it seems harmless, just another visitor from the deep cold between stars. But as more data comes in, its behavior raises questions. Its motion is precise, almost too clean for a random fragment of rock and ice. Its surface reflects light in unusual ways, hinting at something more complex than frozen dust. A few scientists quietly suggest that it might not be natural. Their voices are cautious, their words measured. They know how dangerous it is to make bold claims without proof. Still, the evidence nags at them. If this object was built rather than formed, it was sent by someone. The question is not just who, but why. The answer could be unsettling. In the dark forest's view of the universe, every civilization sees others as potential threats. Space is vast, communication is slow, and intentions are hard to read. A message sent across the stars might take centuries to arrive. By the time a reply is sent, the situation could have changed entirely. This uncertainty makes trust nearly impossible. In such a universe, the safest strategy is silence or preemptive action. Imagine a dense, dark forest at night. Each creature hides in the shadows, listening. If one makes a sound, others hear it. Some may come to investigate, but others may strike first. Assuming danger, the safest way to survive is to stay quiet and strike. Without warning, if another presence is detected. This metaphor captures the logic of the dark forest hypothesis. It suggests that contact between civilizations is inherently risky, and that many may choose to eliminate others before they can grow powerful. If the object in our solar system is a probe from such a civilization, it may not have been sent to communicate. It might have been sent to observe silently, to assess whether we are a threat. Even its arrival could be a test by studying how we react. Our technology, our signals, our defense systems, it could determine whether we pose future danger. The probe itself would not need to act aggressively. Its mere presence could be the first step in a longer chain of decisions far beyond our control. Consider how this would feel on Earth. Nations already struggle to trust one another, even with instant communication and shared history. Misunderstandings happen despite treaties, diplomacy, and surveillance. Now imagine trying to judge the intentions of an alien species light, years away. There are no shared languages, no cultural references, no guarantees. Any signal we send could be interpreted as friendly, neutral, or hostile, depending on how it is read. Even a simple radio message, might sound like a threat to a listener who assumes all unknowns are dangerous. This means the very act of acknowledging the object carries risk. If we send a message to it, or even beam radar toward it, we reveal our position and our capabilities. The probe might record that information and transmit it back to its origin. We cannot know how it would be interpreted. A peaceful transmission might be seen as a display of strength or a declaration of war. Remaining silent, however, has its own dangers. If the probe is here to test for awareness, silence might be read as weakness or vulnerability. Imagine a council of scientists and leaders debating what to do. Some argue for openness, saying we must try to communicate and show peaceful intent. Others insist on total secrecy, fearing that any signal could bring disaster. The debate grows heated as new data comes in. Perhaps the probe changes course slightly or releases small objects. Each action is interpreted through different lenses. Was it a gesture of curiosity or preparation for something worse? With no shared framework, every movement becomes a potential threat. The situation becomes even more tense when we consider timing. If the probe was sent decades or centuries ago, the civilization that launched it may have changed dramatically since then. The decision makers who sent it could be gone. Their goals might no longer apply, or they could have advanced to a point where they see us as primitive and unpredictable. This temporal gap makes interpretation almost impossible. Even if the probe was designed with the best of intentions, its arrival now could trigger events its creators never foresaw. Consider a scenario where the probe's very existence sparks conflict among humans. Governments argue over who controls access to it. Military organizations demand to study it in secret, believing it could contain technology with strategic value. Scientists push for open research, warning that secrecy will only lead to mistakes. In the chaos, someone might take a rash action, attempting to capture or destroy the probe. If the probe's creators are watching, they might interpret that act as aggression. A single impulsive decision could escalate into consequences beyond imagination. The dark forest idea implies that caution is never enough. Even perfect silence cannot guarantee safety. Other civilizations might already know we exist, from our radio emissions or the glow of our cities. If they operate under the assumption that all others are threats, they may act preemptively without warning. The probe we see might be one of many, scattered across the galaxy to monitor emerging civilizations. Some may be dormant, waiting for a signal to activate. Others may have passed through unnoticed centuries ago. Imagine that Earth has already been catalogued. Our broadcasts, our spacecraft, even our patterns of energy use are data points in a vast network to the civilization that built it. We are just one of many species being tracked. Our intentions do not matter. What matters is potential. If our growth continues, we might one day pose a threat to them. This logic feels cold and alien, but it mirrors patterns we know from our own history. When two groups meet under conditions of mistrust and unequal power, the stronger often acts to eliminate the weaker, even when individuals on both sides want peace. Fear can drive conflict. A single misunderstanding can spiral into violence. The difference is that in space, the distances and timescales make it impossible to correct mistakes quickly. By the time a signal crosses light, years, decisions may already have been made. Imagine the probe sending data home, not in real time but as a stored burst of information. Years or centuries from now, another object could arrive based on that data. It might come to act from our point of view. The events would seem disconnected. The first visit would feel like a mystery. The second could arrive without any visible link to the first, leaving us unprepared, even if no second wave ever comes. The psychological effect is profound. The knowledge that we may live in a dark forest changes how we view the universe. Every unexplained signal, every passing object, takes on new weight. We begin to question whether exploration itself is safe. Do we build more powerful telescopes to search for signs of life, or do we deliberately look away, fearing what we might find? The object, silent and indifferent, offers no answers. It continues its path through the solar system, a messenger from a realm we do not understand. Whether it is a warning, a weapon, or simply a relic of another age, we cannot know. All we can do is watch and wonder what choices were made long ago in some distant star system by beings who may view the cosmos not as a place of discovery, but as a battlefield where silence and fear rule. The object appears first as nothing more than a dim point of light. It moves slowly across the sky, too faint for most telescopes to track without special effort. Astronomers plot its path, run their calculations, and share the data. At first, there is no reason to think it is anything unusual. Space is full of debris, ancient rocks, and frozen fragments that drift between stars. But the more they study it, the stranger it seems. Its motion is slightly irregular. Its shape defies expectations. Its surface reflects light in ways that don't fit natural models. These oddities do not prove anything, yet they spark quiet unease. Scientists know that space often surprises them. They have learned to expect the unexpected, but only within certain boundaries. They can imagine ice where they expected rock, or jets of gas where they predicted silence. What they cannot easily imagine is something truly alien, something that does not fit into any category at all. That possibility sits at the edge of their minds, unspoken. As the object draws nearer, more instruments are turned toward it. Radar sweeps, spectral readings, thermal scans. Each new piece of data adds to the puzzle, but the pieces do not fit together. Some readings suggest it is dense and solid, others that it is fragile and hollow. Its speed changes slightly without clear cause. At times, it seems to tumble like a natural body, then its motion steadies, almost as if controlled. The scientists cannot agree on what they are seeing. This uncertainty spreads beyond the labs and observatories. News of the object leaks to the public. At first, people are curious. Even excited, the idea of an interstellar visitor captures the imagination. But as conflicting reports emerge, curiosity turns to fear. Some stories describe a harmless comet. Others hint at a machine built by unknown hands. Social media amplifies every rumor, mixing fact with fantasy, until no one can tell them apart. Governments step in, trying to manage the flow of information. Their statements are careful and vague. They promise that there is no danger while quietly mobilizing resources. Satellites are repositioned. Military units are placed on alert. Behind closed doors, officials debate how to respond. No one has a clear answer, because no one has ever faced a situation like this before. The fear is not just of the object itself, it is fear of what it represents. Humanity has spent centuries imagining contact with other forms of life. In books and movies, we have rehearsed the scenarios over and over. But those stories are shaped by human minds. They assume that alien beings will think in ways we can at least partially understand. The truth may be far stranger. Consider how difficult it is for two human cultures to understand each other. Even with shared biology and similar experiences, miscommunication happens constantly. Words are misunderstood. Actions are misread. Now imagine a being whose senses, motives, and thought processes evolved on another world. Even the most basic assumptions, what it values, what it fears, what it wants, might be unknowable. A gesture meant as peace could be seen as hostility. A defensive move could trigger aggression. The greatest danger may not come from advanced weapons or hidden technology, but from ourselves. If we cannot interpret what we are seeing, our reactions may be guided by fear rather than reason. A single mistake, made in panic, could escalate into catastrophe. Imagine a meeting of world leaders as the object approaches. The data is incomplete and contradictory. Some advisors urge caution, arguing that no action should be taken until more is known. Others insist on immediate preparation for defense. Rumors swirl that rival nations are secretly planning to capture or destroy the object. Trust breaks down, each country begins to act independently, taking steps that others interpret as threats. In this atmosphere, even a minor event could spark chaos. Suppose the object emits a brief burst of radio noise. It could be a natural release of energy, or an attempt at communication, or simply a malfunction. With no clear understanding, each group interprets it through their own fears. One nation sees it as a hostile signal and prepares a military response. Another views the response as aggression and reacts in kind. Within hours, the focus shifts from the object to human conflict. As old rivalries flare under new pressure, the dread deepens because humans have faced disasters before: plagues, earthquakes, wars. In each case, the threat came from something we could ultimately understand, even if it took time. A virus follows biological rules. A hurricane follows atmospheric ones. But a truly alien presence might operate according to principles we cannot even describe. Imagine trying to explain a smartphone to a person living thousands of years ago. They would not have the concepts needed to grasp what it is. Now reverse that perspective. If the object carries systems beyond our comprehension, we may misinterpret their purpose completely. What we see as a harmless sensor could be a weapon. What we think is a random movement could be a deliberate signal. Our lack of understanding turns every observation into a potential source of error. This ignorance shapes our emotions as well as our actions. Humans seek patterns and meaning. When faced with the unknown, we fill gaps with stories. Some of these stories may be hopeful, dreams of contact and cooperation. Others may be dark, full of suspicion, and the problem is that both kinds are guesses. Acting on them is like walking blindfolded across a cliff edge. Consider an ordinary citizen watching the news as events unfold. One channel says the object is harmless. Another warns of invasion. Online forums argue over every rumor. Each claiming secret knowledge, the person does not know whom to trust. Anxiety builds. They make choices about their family, their job, their future, based on fragments of unreliable information. Multiply this confusion by millions, and entire societies can become unstable. Even within the scientific community, fear can take subtle forms. Researchers may become so cautious that they stop asking bold questions. They avoid theories that might be labeled reckless or alarming. As a result, the very ideas that could lead to understanding are never explored. Curiosity, the engine of discovery, slows under the weight of collective anxiety. The object itself may do nothing overt. It might simply pass through the solar system and leave again, silent and indifferent. But its mere presence forces humanity to confront its own limits. We realize how fragile our systems of knowledge are, how easily our assumptions can fail. The universe is vast and strange, and we are small within it. Imagine the moment when the object is closest to Earth. Telescopes capture its image in sharp detail. Instruments record every signal and reflection. Yet even with this flood of data, the core mystery remains unsolved. The object does not fit into any familiar category. The questions it raises are too large for the answers we have. In that moment, the fear is not of attack or destruction. It is the fear of standing before something we cannot comprehend, knowing that our next move might shape the fate of our species. As it drifts away, the object leaves behind more than physical traces. It leaves a deep uncertainty. Humans are used to seeing themselves as explorers and problem solvers. This event forces us to consider that we may not be ready, not in our technology, not in our politics, and not in our minds. The real threat is not the unknown itself, but our inability to face it without breaking under its weight.